Earth's seasons are caused primarily by the tilt of Earth's axis, not by changes in distance from the sun. And this single geometric fact quietly governs the rhythm of climate, light, temperature, and life across the planet in a way that is both subtle and profound. Because although Earth travels around the sun in a slightly oval-shaped path, the small variation in distance is far too minor to explain the dramatic differences between summer warmth and winter cold. And instead, the defining influence is the steady 23.5-degree tilt of Earth's rotational axis, which remains pointed in nearly the same direction throughout the year as the planet orbits, causing sunlight to strike different regions at different angles and for different durations. And this change in angle determines how concentrated or spread out solar energy becomes when it reaches the surface, meaning that when sunlight arrives more directly, it delivers greater energy per unit area, warming land, oceans, and atmosphere more efficiently, while when sunlight arrives at a shallow angle, it is dispersed across a wider surface, reducing its heating power and creating cooler conditions. And this contrast explains why summer is warm not because Earth is closer to the sun, but because a hemisphere is tilted toward it, receiving longer days and higher sun angles, and why winter is cold not because Earth has moved away, but because that same hemisphere is tilted away, receiving shorter days and lower sun angles, allowing heat to dissipate more easily than it is gained. And this tilt-driven mechanism operates with remarkable consistency, shaping predictable seasonal cycles that repeat year after year, even as weather patterns fluctuate from day to day. And as Earth rotates daily, the tilted axis ensures that the sun traces different paths across the sky depending on the time of year, rising higher and staying longer during summer months and remaining lower and briefer during winter months, subtly controlling how much solar energy accumulates over time. And this accumulation, rather than instantaneous distance, is what determines seasonal warmth, allowing soils to heat, plants to grow, snow to melt, and oceans to store energy that is later released, moderating climates and influencing atmospheric circulation. And this explanation corrects a common misunderstanding, because many people intuitively assume that summer occurs when Earth is closer to the sun, and winter when it is farther away. Yet in reality, Earth reaches its closest point to the sun during early January, when the northern hemisphere is in winter, and its farthest point during early July, when that hemisphere experiences summer, demonstrating clearly that distance is not the controlling factor, and instead reinforcing that the tilt governs how sunlight is distributed across latitudes, creating opposite seasons in opposite hemispheres, so that when the northern hemisphere leans toward the sun, the southern hemisphere leans away, and vice versa, producing a global balance in which heat, light, and energy are shared across the planet over the course of the year. And this alternating exposure not only defines temperature patterns, but also regulates biological timing, because plants, animals, and even microorganisms respond more strongly to changes in daylight length than to temperature alone, using the predictable signal of longer or shorter days to trigger flowering, migration, reproduction, dormancy, and hibernation. And this reliability exists because axial tilt changes only very slowly over tens of thousands of years, providing a stable environmental clock around which life has evolved intricate adaptations. And as sunlight angles shift gradually from day to day, they create smooth transitions rather than abrupt changes, allowing ecosystems to adjust incrementally as seasons unfold. And this gentle progression is why spring and autumn exist as transitional phases, rather than sudden switches between extremes, because the tilt causes a slow redistribution of solar energy rather than an on-off mechanism. And as Earth continues its orbit, every latitude experiences its own version of this effect, with regions near the equator receiving relatively consistent sunlight year-round, and therefore experiencing weaker seasonal contrasts, while regions closer to the poles experience dramatic variations in daylight, including periods of continuous daylight or darkness, illustrating how the same axial tilt produces vastly different seasonal experiences depending on geographic location, yet remains governed by the same underlying principle. And this tilt-driven system also interacts with Earth's rotation, atmosphere, and oceans, amplifying or moderating seasonal effects through winds, currents, and heat transport, but always rooted in the initial distribution of sunlight. And as energy is absorbed during long summer days, it is stored in land and water, slowly released during cooler months, smoothing extremes and sustaining life even when direct sunlight weakens. And this delayed response further explains why the warmest and coldest days typically lag behind solstices, showing that seasons are not instantaneous reactions but cumulative outcomes of energy balance over time. And by understanding that tilt, not distance, is the primary cause of seasons, we gain a clearer appreciation of Earth as a dynamic system governed by geometry and motion rather than proximity alone, revealing how simple physical principles give rise to complex environmental patterns. And this realization deepens our sense of connection to the planet's rhythms, because every sunrise, shadow length, and seasonal shift reflects the same quiet alignment between Earth's axis and its orbital path. And recognizing this alignment encourages a more patient, observational mindset, one that sees change not as abrupt or chaotic, but as the natural result of steady movement through space, where the angle of light gradually transforms landscapes, climates, and living systems. And in this way, the tilt of Earth's axis becomes more than a scientific detail, becoming instead a reminder that balance, timing, and orientation shape experience more profoundly than simple distance, guiding the cyclical story of seasons that has repeated unbroken for millions of years, and continues to quietly define the conditions for life today. Earth's axis is tilted at about 23.5 degrees, a seemingly small angle that quietly governs the structure of seasons, climate patterns, and the long-term stability of life on the planet, because this tilt determines how sunlight is distributed across Earth's surface as it moves through space, and without it, the planet would experience a vastly different and far less dynamic environment, one in which seasonal variation would be minimal, and many ecological rhythms would not exist. And this tilt is measured relative to Earth's orbital plane, meaning that instead of standing upright like a spinning top, Earth leans slightly as it rotates, causing one hemisphere to receive more direct sunlight for part of the year, while the other receives less. And although 23.5 degrees may sound modest, its effects are amplified by the immense scale of Earth's surface and the constant influx of solar energy, allowing small geometric differences to produce large climatic contrasts over time. And this tilt remains remarkably stable over human timescales, changing only very slowly due to gravitational interactions with the Moon and other planets, which means that the seasonal cycle has remained broadly consistent for thousands of years, providing a reliable framework within which ecosystems and civilizations have developed. And as Earth orbits the Sun, the axis maintains its orientation toward a fixed point in space, causing the angle of sunlight to shift gradually across latitudes. And this gradual shift is what creates the smooth progression from winter to spring, to summer to autumn, rather than abrupt transitions, allowing biological systems to adapt incrementally rather than being forced into sudden change. And the tilt ensures that during summer in one hemisphere, the sun climbs higher in the sky, stays above the horizon longer, and delivers energy more directly, while during winter the sun remains lower, daylight hours shorten, and energy arrives at a shallower angle, spreading across a larger area and producing cooler conditions. And this difference in solar angle affects not only temperature, but also atmospheric circulation, because warmer regions experience rising air and shifting pressure systems that drive winds, storms, and precipitation patterns, all of which are ultimately rooted in how the tilt distributes sunlight. And if Earth's axis were not tilted at all, each latitude would receive nearly the same amount of sunlight throughout the year, eliminating true seasons and creating a static climate pattern where temperature differences between summer and winter would be minimal. And while such a world might still support life, it would lack the diversity of seasonal cues that many organisms depend on for reproduction, migration, and survival. And conversely, If Earth's tilt were much greater, seasons would become far more extreme, with hotter summers and colder winters, potentially destabilizing ecosystems and making large regions inhospitable for complex life, showing that the current tilt represents a delicate balance that supports long-term habitability, and this balance extends beyond temperature alone, because the tilt also influences ice formation, snow cover, and the reflectivity of Earth's surface, known as albedo, which feeds back into climate by determining how much sunlight is absorbed versus reflected back into space. And during winter months, increased snow and ice reflect more sunlight, reinforcing cooling, while during summer months, darker land and ocean surfaces absorb more energy, reinforcing warming, and these feedback loops operate within the framework established by the axial tilt, demonstrating how a single geometric parameter can shape a complex self-regulating system. And over geological timescales, slight variations in the tilt, known as obliquity changes, contribute to long-term climate cycles such as ice ages, showing that even small adjustments to this angle can have profound consequences when integrated over thousands of years. And this sensitivity highlights the importance of stability, because Earth's tilt oscillates within a relatively narrow range, preventing runaway climate extremes while still allowing enough variation to drive natural cycles of glaciation and warming. And the presence of the Moon plays a critical role in maintaining this stability, because its gravitational influence dampens large fluctuations in Earth's tilt, acting as a stabilizing force that has helped preserve consistent seasonal patterns over billions of years. And without this stabilizing influence, Earth's tilt might vary chaotically, leading to unpredictable climates that could challenge the persistence of complex ecosystems. And the tilt also shapes human experience in subtle yet profound ways, influencing agricultural cycles, cultural calendars, and historical patterns of settlement, because societies have long depended on predictable seasonal changes to determine planting times, harvests, and resource availability. Why? And many ancient cultures built monuments, calendars, and rituals aligned with solstices and equinoxes, reflecting an intuitive recognition of the axial tilt's role in structuring time and meaning. And even in the modern world, the tilt continues to govern energy demand, water availability, and food production, linking a cosmic geometric property directly to daily human life. And beyond practical considerations, the tilt offers a deeper perspective on Earth's place in space, reminding us that the rhythms we experience are not random but arise from the planet's orientation and motion within the solar system. And by understanding that a stable 23.5-degree tilt underlies the changing length of days, the shifting position of the sun, and the recurring pattern of seasons, we gain a sense of continuity that connects present experience with deep time. Because this same tilt influenced the climate experienced by early life, shaped the environments in which humans evolved, and continues to operate unchanged as generations pass. And this continuity fosters a sense of calm and perspective, showing that beneath the variability of weather and the unpredictability of daily events lies a steady, enduring structure that unfolds with quiet precision. And as sunlight traces its annual path across the sky, rising higher and lower in response to the axial tilt, it silently marks the passage of time, turning Earth's rotation and orbit into a cosmic clock that regulates life, climate, and consciousness. And in recognizing the central role of Earth's 23.5-degree tilt, we come to see seasons not as arbitrary divisions of the calendar, but as expressions of a deeper alignment between planet and star, an alignment that has shaped the planet's past, sustains its present, and will continue to guide its future as long as Earth spins beneath the sun. This axial tilt causes different parts of TH to receive varying angles of sunlight throughout the year, and this variation is the fundamental mechanism behind seasonal change, because the angle at which sunlight strikes Earth's surface determines how concentrated or dispersed solar energy becomes, shaping temperature, atmospheric behavior, and ecological rhythms across the planet. And as Earth orbits the sun, The tilted axis ensures that the sun's apparent path across the sky slowly shifts northward and southward, changing how directly its rays strike each latitude. And when sunlight arrives at a steep angle, it is concentrated into a smaller surface area, delivering more energy per square meter, while shallow angles spread the same energy over a wider area, reducing heating efficiency. And this geometric reality explains why tropical regions near the equator remain warm year-round, while higher latitudes experience strong seasonal contrasts. Because near the equator the sun remains relatively high in the sky throughout the year, whereas closer to the poles the sun's height changes dramatically between summer and winter. And this difference in solar angle interacts with Earth's rotation to produce daily cycles of heating and cooling that vary in intensity with the seasons, creating longer, warmer days in summer and shorter, cooler days in winter. And beyond temperature alone, the angle of sunlight influences how energy penetrates the atmosphere, because sunlight arriving at a shallow angle must travel through a thicker layer of air, scattering more energy and reducing the amount that reaches the surface, while steeply angled sunlight passes through less atmosphere and arrives with greater intensity, reinforcing seasonal contrasts. And this atmospheric filtering effect is especially noticeable during winter at higher latitudes, where low sun angles result in dimmer light, longer shadows, and weaker heating eve. And on clear days, and these optical and energetic differences subtly shape human perception of the seasons, influencing mood, behavior, and cultural associations with light and darkness. And as Earth continues its orbit, the shifting angle of sunlight also alters how energy is distributed between land and ocean, because land heats and cools more rapidly than water, leading to seasonal pressure differences that drive monsoons, prevailing winds, and large-scale circulation patterns. And these circulation patterns redistribute heat and moisture around the globe, linking the angle of sunlight in one region to weather conditions thousands of kilometers away, demonstrating how a simple geometric change can propagate through complex systems. And the seasonal variation in sunlight angle also controls the timing of snowmelt, ice formation, and plant growth, because the amount of energy received determines when temperatures rise above freezing and when photosynthesis becomes efficient enough to support new growth. And, in temperate regions, the gradual increase in sun angle during spring triggers a cascade of biological responses, from budding leaves to migrating animals, all synchronized to the slow, predictable shift of solar geometry. And this synchronization illustrates how deeply life is attuned to the physical structure of Earth's orbit and tilt, responding not to abstract calendar dates, but to the actual angle and duration of sunlight. And as summer approaches, higher sun angles lengthen daylight hours, increase energy input, and drive peak biological productivity, while as autumn arrives, declining angles reduce energy, signaling organisms to store resources, migrate, or enter dormancy. And this seasonal choreography depends on the reliability of sunlight angle changes, which have remained consistent over millennia, allowing evolutionary processes to encode these patterns into genetic and behavioral traits. And the variation in sunlight angle also affects the color and quality of light, because lower angles enhance scattering of shorter wavelengths, producing warmer hues during sunrise, sunset, and winter days, subtly altering visual environments and contributing to the aesthetic experience of seasons. And these changes in light quality influence not only human perception, but also animal navigation and plant development, as many species use light cues to regulate circadian and seasonal rhythms. And at extreme latitudes, the consequences of changing sunlight angles become even more pronounced, leading to phenomena such as the midnight sun and polar night, where the sun remains continuously above or below the horizon for extended periods, creating environments defined by prolonged light or darkness rather than daily cycles. And these extremes highlight the full range of effects produced by Earth's tilt, demonstrating how a single planetary parameter can generate immense diversity in lived experience across latitudes. And despite these extremes, the gradual nature of sunlight angle changes provides continuity, allowing ecosystems to adjust progressively rather than abruptly. And this gradualism contributes to Earth's long-term stability, because sudden shifts in energy input would challenge the resilience of life and climate systems. And over longer timescales, variations in Earth's orbit subtly modulate how sunlight angles change year to year, contributing to cycles of warming and cooling that shape geological and biological history. Yet these variations operate within the broader framework set by the axial tilt, reinforcing its central role. And by understanding how different angles of sunlight arise from Earth's orientation in space, we gain insight into why seasons unfold as smooth transitions rather than sharp boundaries. And this understanding fosters a deeper appreciation of the quiet precision underlying everyday experience, because each sunrise, shadow length, and seasonal temperature shift reflects a consistent geometric relationship between Earth and Sun, and this relationship connects the immediate sensations of warmth, light, and time to cosmic motion, reminding us that daily life is embedded within planetary scale processes. And as we observe sunlight moving higher or lower in the sky across weeks and months, we witness the tangible expression of Earth's tilt, a slow, graceful adjustment that shapes climate, ecosystems, and human culture without conscious intervention. And this awareness can inspire a sense of calm and continuity, because it reveals that beneath the apparent variability of weather lies a steady, predictable pattern governed by geometry and motion. And in recognizing how varying angles of sunlight orchestrate the seasons, we see Earth not as a static backdrop, but as a dynamic system, gently rotating and orbiting, translating cosmic alignment into the rhythms of life, growth, rest, and renewal that define existence on the planet. The changing length of daylight across the year is one of the most immediately noticeable consequences of Earth's tilt and orbit, and it plays a central role in shaping seasonal experience, biological rhythms, and climatic behavior, because daylight duration directly controls how long solar energy is delivered to a given location each day. And this temporal dimension of sunlight works alongside solar angle to determine total energy input, meaning that seasons are defined not only by how high the sun rises, but also by how long it remains above the horizon. And as Earth moves along its orbit, the tilted axis causes one hemisphere to lean toward the sun while the other leans away, gradually lengthening days in one hemisphere while shortening them in the other. And this process unfolds smoothly over weeks and months, creating the familiar progression from short winter days to long summer days and back again. And at the equinoxes, when Earth's axis is oriented sideways relative to the sun, day and night are nearly equal everywhere on the planet, marking transitional moments when neither hemisphere is favored. And these moments divide the year into symmetrical halves that anchor seasonal calendars across cultures. And following the equinoxes, daylight continues to increase in one hemisphere until it reaches a maximum at the summer solstice, when the sun appears to pause before reversing its motion, producing the longest day and shortest night of the year. And this extended daylight allows solar energy to accumulate over many hours, driving peak temperatures, accelerating biological growth, and enhancing atmospheric circulation. And after the solstice, daylight slowly decreases, signaling the gradual decline of summer and the approach of autumn. And this slow reduction in light duration acts as a powerful cue for living systems, because many organisms rely more on day length and temperature to regulate seasonal behaviors, ensuring that biological timing remains consistent even when weather varies unpredictably. And plants use changes in daylight to trigger flowering, leaf drop, and dormancy, while animals use it to initiate migration, reproduction, and hibernation, embedding Earth's orbital geometry directly into life cycles. And in humans, changing daylight influences sleep patterns, mood, and energy levels through hormonal pathways that respond to light exposure, illustrating how deeply the seasonal light cycle is integrated into physiology and psychology. And at higher latitudes, the variation in daylight becomes more extreme, with summer days stretching toward continuous light and winter days shrinking toward darkness. amplifying seasonal contrasts and shaping distinctive cultural adaptations, such as altered work schedules, architectural design, and social traditions that accommodate long days or long nights. And these adaptations reflect humanity's capacity to respond creatively to the predictable yet powerful influence of daylight variation. And the persistence of these patterns over generations reinforces cultural continuity, because communities learn to anticipate and plan around the seasonal light cycle rather than reacting to it unpredictably. And the predictability of daylight change is a direct consequence of Earth's stable axial tilt and regular orbit, which together create a reliable annual rhythm that has remained essentially unchanged for thousands of years. And this reliability has allowed agricultural societies to synchronize planting and harvesting with daylight availability, maximizing productivity by aligning human activity with natural energy cycles. And even in modern industrial societies, daylight length continues to influence energy consumption, transportation patterns, and economic activity. As longer days reduce artificial lighting needs and encourage outdoor movement, while shorter days increase reliance on stored energy in indoor environments. And beyond practical impacts, the changing length of daylight shapes emotional and symbolic associations with the seasons, because light has long been linked to concepts of growth, clarity, and renewal, while darkness has been associated with rest, reflection, and conservation. And these associations are reinforced each year as daylight waxes and wanes, embedding cosmic motion into language, art, and storytelling. And the gradual nature of daylight change is particularly important, because it allows both ecosystems and human societies to adjust incrementally rather than facing abrupt transitions, reducing stress and increasing resilience. And this gradualism reflects a broader principle in Earth's systems, where slow, continuous processes dominate over sudden shifts, promoting long-term stability. And the interplay between daylight duration and solar angle also explains why the hottest and coldest temperatures lag behind the solstices. Because even after daylight begins to shorten, accumulated heat continues to build until energy input and loss reach a new balance, demonstrating how seasonal effects integrate over time, rather than responding instantaneously. And this thermal inertia further smooths seasonal transitions, preventing extreme volatility and supporting ecological balance. And the lengthening and shortening of days also affect atmospheric chemistry, because sunlight drives photochemical reactions that influence ozone formation, air quality, and cloud behavior, linking daylight duration to environmental conditions that extend beyond temperature alone. And over geological timescales, variations in Earth's orbit slightly alter the timing and intensity of daylight changes, contributing to long-term climate cycles. Yet these variations remain bounded by the fundamental geometry of tilt and orbit, preserving the overall structure of the seasonal light cycle. And this preservation has allowed life to evolve complex dependencies on light timing without being undermined by chaotic variation. And from a broader perspective, the changing length of daylight transforms Earth's rotation and revolution into a living clock, one that measures time not with numbers, but with shifting illumination, guiding biological, cultural, and climatic processes with silent precision. And each sunrise and sunset becomes a marker within this larger cycle, reminding observers that daily experience is nested within annual motion, and annual motion within cosmic order. And by recognizing the waxing and waning of daylight arise from Earth's orientation in space, rather than from changes in distance to the sun, we gain a clearer understanding of seasonal mechanics, dispelling common misconceptions, while deepening appreciation for the elegance of planetary motion. And this understanding invites reflection, because it reveals that the rhythms shaping life are neither arbitrary nor fragile, but arise from stable, enduring relationships between Earth and Sun. And as daylight stretches and contracts year after year, it weaves continuity through time, connecting past, present, and future in a repeating yet ever-renewing pattern. And this pattern fosters patience and perspective, showing that change does not always require disruption, but can unfold gently through predictable cycles. And ultimately, the changing length of daylight stands as one of the clearest expressions of Earth's seasonal story, translating tilt and orbit into lived experience, shaping climate and consciousness alike, and offering a steady, luminous rhythm that guides life forward through the turning year. The changing length of daylight across the year is one of the most immediately noticeable consequences of Earth's tilt and orbit, and it plays a central role in shaping seasonal experience, biological rhythms, and climatic behavior, because daylight duration directly controls how long solar energy is delivered to a given location each day. And this temporal dimension of sunlight works alongside solar angle to determine total energy input, meaning that seasons are defined not only by how high the sun rises, but also by how long it remains above the horizon. And as Earth moves along its orbit, the tilted axis causes one hemisphere to lean toward the sun while the other leans away, gradually lengthening days in one hemisphere while shortening them in the other, and this process unfolds smoothly over weeks and months, creating the familiar progression from short winter days to long summer days and back again. And at the equinoxes, when Earth's axis is oriented sideways relative to the sun, day and night are nearly equal everywhere on the planet, marking transitional moments when neither hemisphere is favored. And these moments divide the year into symmetrical halves that anchor seasonal calendars across cultures. And following the equinoxes, daylight continues to increase in one hemisphere until it reaches a maximum at the summer solstice, when the sun appears to pause before reversing its motion, producing the longest day and shortest night of the year. And this extended daylight allows solar energy to accumulate over many hours, driving peak temperatures, accelerating biological growth, and enhancing atmospheric circulation. And after the solstice, daylight slowly decreases, signaling the gradual decline of summer and the approach of autumn. And this slow reduction in light duration acts as a powerful cue for living systems, because many organisms rely more on day length than temperature to regulate seasonal behaviors, ensuring that biological timing remains consistent even when weather varies unpredictably, and plants use changes in daylight to trigger flowering, leaf drop, and dormancy, while animals use it to initiate migration, reproduction, and hibernation, embedding Earth's orbital geometry directly into life cycles. And in humans, changing daylight influences sleep patterns, mood, and energy levels through hormonal pathways that respond to light exposure, illustrating how deeply the seasonal light cycle is integrated into physiology and psychology. And at higher latitudes, the variation in daylight becomes more extreme, with summer days stretching toward continuous light and winter days shrinking toward near darkness, amplifying seasonal contrasts and shaping distinctive cultural adaptations, such as altered work schedules, architectural design, and social traditions that accommodate long days or long nights. And these adaptations reflect humanity's capacity to respond creatively to the predictable yet powerful influence of daylight variation. And the persistence of these patterns over generations reinforces cultural continuity, because communities learn to anticipate and plan around the seasonal light cycle rather than reacting to it unpredictably. And the predictability of daylight change is a direct consequence of Earth's stable axial tilt and regular orbit, which together create a reliable annual rhythm that has remained essentially unchanged for thousands of years. And this reliability has allowed agricultural societies to synchronize planting and harvesting with daylight availability, maximizing productivity by aligning human activity with natural energy cycles. And even in modern industrial societies, daylight length continues to influence energy consumption, transportation patterns, and economic activity, as longer days reduce artificial lighting needs and encourage outdoor movement, while shorter days increase reliance on stored energy and indoor environments. And beyond practical impacts, the changing length of daylight shapes emotional and symbolic associations with the seasons, because light has long been linked to concepts of growth, clarity, and renewal, while darkness has been associated with rest, reflection, and conservation. And these associations are reinforced each year as daylight waxes and wanes, embedding cosmic motion into language, art, and storytelling. And the gradual nature of daylight change is particularly important because it allows both ecosystems and human societies to adjust incrementally, rather than facing abrupt transitions, reducing stress and increasing resilience. And this gradualism reflects a broader principle in Earth's systems, where slow, continuous processes dominate over sudden shifts, promoting long-term stability. And the interplay between daylight duration and solar angle also explains why the hottest and coldest temperatures lag behind the solstices. Because even after daylight begins to shorten, accumulated heat continues to build until energy input and loss reach a new balance, demonstrating how seasonal effects integrate over time rather than responding instantaneously. And this thermal inertia further smooths seasonal transitions, preventing extreme volatility and supporting ecological balance. And the lengthening and shortening of days also affect atmospheric chemistry, because sunlight drives photochemical reactions that influence ozone formation, air quality, and cloud behavior, linking daylight duration to environmental conditions that extend beyond temperature alone. And over geological timescales, variations in Earth's orbit slightly alter the timing and intensity of daylight changes, contributing to long-term climate cycles. Yet these variations remain bounded by the fundamental geometry of tilt and orbit, preserving the overall structure of the seasonal light cycle. And this preservation has allowed life to evolve complex dependencies on light timing without being undermined by chaotic variation. And from a broader perspective, the changing length of daylight transforms Earth's rotation and revolution into a living clock, one that measures time not with numbers but with shifting illumination, guiding biological, cultural, and climatic processes with silent precision. And each sunrise and sunset becomes a marker within this larger cycle, reminding observers that daily experience is nested within annual motion, and annual motion within cosmic order. And by recognizing that the waxing and waning of daylight arise from Earth's orientation in space rather than from changes in distance to the sun, we gain a clearer understanding of seasonal mechanics, dispelling common misconceptions while deepening appreciation for the elegance of planetary motion. And this understanding invites reflection, because it reveals that the rhythms shaping life are neither arbitrary nor fragile, but arise from stable, enduring relationships between Earth and Sun. And as daylight stretches and contracts year after year, it weaves continuity through time, connecting past, present, and future in a repeating, yet ever-renewing pattern. And this pattern fosters patience and perspective, showing that change does not always require disruption, but can unfold gently through predictable cycles. And ultimately, the changing length of daylight stands as one of the clearest expressions of Earth's seasonal story, translating tilt and orbit into lived experience, shaping climate and consciousness alike, and offering a steady, luminous rhythm that guides life forward through the turning year. As Earth orbits the Sun, the tilted axis always points in nearly the same direction in space, and this quiet constancy is one of the most important yet least noticed features of the seasonal system, because it ensures that the pattern of seasons unfolds predictably year after year, rather than fluctuating randomly. And this fixed orientation means that Earth does not wobble back and forth as it travels along its orbital path, but instead maintains a steady lean, much like a spinning top whose axis remains pointed toward a distant reference point. And in Earth's case, that reference lies near the direction of the North Star, allowing the planet to present different hemispheres toward the Sun at different times of year, while preserving the same overall alignment. And this stability is what allows sunlight to migrate gradually across latitudes rather than jumping abruptly, producing smooth seasonal transitions that ecosystems and climates can adapt to. And as Earth moves from one side of its orbit to the other, the hemisphere tilted toward the Sun changes, but the direction of the tilt itself does not, creating a rhythmic alternation between hemispheres that defines the annual cycle. And this mechanism explains why seasons repeat with such regularity. because the geometry resets itself every year without needing any additional force or adjustment, and this consistency is reinforced by Earth's rotation, which continues uninterrupted beneath the tilted axis, turning the planet once every 24 hours and allowing sunlight to sweep across the surface daily while the seasonal pattern unfolds slowly in the background. And this layering of motions, daily rotation combined with annual revolution, creates a complex yet orderly system in which short-term cycles are nested within longer-term ones, providing both stability and variation. And the fact that Earth's axis points in the same direction throughout its orbit also explains why the sun's apparent path across the sky shifts predictably from season to season, rising and setting at different points along the horizon and reaching different heights at noon, because these changes are driven by Earth's changing position relative to the sun, while the axial orientation remains fixed. And this predictability has allowed humans to track time and seasons long before modern science, using the positions of the sun, stars, and shadows as reliable indicators of Earth's motion. And ancient structures aligned with solstices and equinoxes demonstrate an intuitive understanding of this fixed axial orientation, even without formal knowledge of orbital mechanics. And beyond cultural significance, the steady direction of Earth's axis plays a crucial role in climate regulation, because it prevents chaotic shifts in solar exposure that would destabilize atmospheric and oceanic circulation, and instead provides a stable framework within which winds, currents, and weather patterns can organize themselves, and this organization allows energy to be redistributed efficiently around the planet, smoothing temperature differences and supporting diverse climates. And the stability of the axial orientation is not accidental, because it is maintained in part by the gravitational influence of the Moon, which acts as a stabilizing partner, damping large variations in tilt that could otherwise arise from gravitational interactions with other planets. And without this stabilizing effect, Earth's axis might wander significantly over time, leading to extreme and unpredictable seasonal changes that could challenge the persistence of complex life. And thus the fixed direction of the axis represents not only a mechanical feature, but a foundation for long-term habitability. And over very long timescales, the axis does undergo slow W movements such as precession, a gradual wobble that traces a circular path over tens of thousands of years. Yet even this motion is slow enough that it does not disrupt the basic seasonal pattern within human or even historical timescales, allowing civilizations to rise and fall under essentially the same seasonal structure. And this endurance fosters continuity because generations experience familiar cycles of light and temperature, anchoring memory, tradition, and planning. And the fixed axial orientation also ensures symmetry in the seasonal system, because it guarantees that when one hemisphere experiences summer, the other experiences winter, maintaining a global balance in energy distribution. And this balance is essential for the functioning of Earth's climate, because it drives large-scale circulation patterns that transport heat from equatorial regions toward the poles, preventing excessive buildup of energy in any one area. And these circulation patterns depend on the predictability of solar input, which in turn depends on the steady axial alignment. And at a more subtle level, the constancy of the axis contributes to the reliability of biological clocks, because organisms evolve in response to consistent environmental cues, and the stable orientation of Earth's axis ensures that day length, solar angle, and seasonal timing remain consistent enough for life to synchronize internal rhythms with external cycles. And this synchronization supports efficient energy use, reproduction, and survival, reinforcing the link between planetary mechanics and biological function. And the fact that Earth's axis points in the same direction throughout its orbit also creates a sense of continuity in the sky, because the stars visible at night change gradually with the seasons, reflecting Earth's changing position, while the axial orientation preserves a stable frame of reference. And this gradual shift has been used historically to mark the passage of the year, further embedding axial stability into human understanding of time. And when viewed from space, Earth's motion appears serene and orderly, a planet leaning steadily as it traces a gentle path around its star, translating cosmic geometry into seasonal experience without abrupt change. And this serenity contrasts with the dynamic and sometimes chaotic nature of weather, reminding us that variability at one scale can coexist with stability at another. And this layered stability offers a powerful metaphor for balance, suggesting that enduring orientation can support dynamic expression without collapse. And as sunlight moves north and south across the globe in response to Earth's fixed tilt, it paints the planet with shifting patterns of warmth, growth, and rest, creating a living mosaic that changes predictably, yet never repeats exactly. And this combination of repetition and variation is central to Earth's seasonal story, because it provides enough regularity to support life while allowing enough diversity to foster adaptation and complexity. And by understanding that Earth's axis maintains its direction in space as the planet orbits the Sun, we gain insight into why seasons are reliable, why calendars work, and why climate patterns have coherence across time. And this understanding deepens appreciation for the quiet precision of planetary motion, revealing that beneath the surface of daily experience lies a stable geometric relationship, guiding the flow of energy and time. And in recognizing this, we are reminded that the rhythms shaping life are not fragile coincidences, but expressions of enduring alignment, sustained over immense spans of time. And as Earth continues its journey around the Sun, leaning steadily, it carries with it the promise of return, the assurance that light, ill wax and wane in familiar ways, and that seasons will follow one another in a rhythm that has guided the planet for millions of years, and will continue to do so far into the future. Because Earth's axis maintains its fixed orientation in space as the planet orbits the Sun, one hemisphere gradually leans toward the Sun while the other leans away. And this slow, continuous change in orientation relative to incoming sunlight is what creates the alternating pattern of seasons between the northern and southern hemispheres, a pattern that unfolds with quiet regularity and remarkable balance. Because as Earth moves along its orbital path, the hemisphere tilted toward the Sun receives sunlight at higher angles and for longer durations, while the opposite hemisphere receives sunlight at lower angles and for shorter durations. And this contrast in solar exposure produces simultaneous but opposite seasonal conditions across the globe, ensuring that when summer unfolds in one hemisphere, winter takes hold in the other. And this opposition is not incidental but an inevitable consequence of Earth's axial geometry, reflecting how a single orientation can generate complementary experiences on opposite sides of the planet. And this hemispheric alternation plays a crucial role in regulating Earth's overall energy balance, because it prevents excessive heating or cooling from becoming concentrated in one region for extended periods, and instead distributes solar energy more evenly over time, allowing the planet to maintain long-term climatic stability. And as one hemisphere warms and expands its atmosphere during summer, the other cools and contracts during winter, creating pressure gradients that drive large-scale wind systems and ocean currents, linking the seasonal states of each hemisphere into a connected global system. And this interconnection means that seasonal changes are never isolated, but always part of a planetary scale exchange of energy and motion. And the alternation of hemispheric seasons also shapes ecological patterns, because species have evolved to take advantage of predictable cycles of abundance and scarcity, timing growth, reproduction, and migration to coincide with favorable conditions. And these patterns often operate in opposite phases between hemispheres, creating a global mosaic of biological activity that shifts throughout the year. And for migratory species, this alternation provides opportunities to move between hemispheres or latitudes, to remain within preferred environmental conditions, effectively following the Sun's path across the planet. And this movement illustrates how life responds dynamically to the geometric structure of Earth's orbit, translating axial tilt into behavioral strategy. And human societies have likewise adapted to hemispheric seasonality, developing agricultural calendars, cultural traditions, and economic rhythms aligned with local seasonal cycles, while also engaging in global trade that bridges hemispheric differences, such as transporting food and resources from regions in harvest to regions in winter. And this exchange underscores how the alternating seasons create both diversity and interdependence, encouraging cooperation across geographic boundaries. And the hemispheric opposition of seasons also influences the distribution of ice and snow, because when one hemisphere experiences winter and accumulates snow cover, the other experiences summer melt, preventing simultaneous maximum ice growth in both hemispheres and contributing to the moderation of global sea levels and climate. And the staggered pattern is another example of how axial tilt promotes balance rather than extremes. And at the poles, the effects of hemispheric leaning become especially pronounced, producing months of sea, continuous daylight or darkness that define polar environments and drive unique adaptations in organisms capable of surviving such extremes. And these polar conditions mirror one another across hemispheres, reinforcing the symmetry inherent in Earth's seasonal design. And the gradual shift of hemispheric orientation also ensures that seasonal transitions are smooth rather than abrupt, because Earth does not suddenly switch which hemisphere faces the sun, but instead moves continuously along its orbit, allowing sunlight distribution to change incrementally. And this gradualism supports resilience, because ecosystems and climates can adjust over time rather than being forced into sudden change. And this resilience has been essential for the long-term persistence of life, which depends on reliable patterns more than on static conditions. And the alternation of hemispheric seasons also has subtle psychological and cultural effects, because human perceptions of time, renewal, and rest are often shaped by seasonal contrast, and knowing that seasons are reversed elsewhere on the planet can foster a sense of global perspective, reminding us that local experience is part of a larger, interconnected system. And this awareness becomes especially relevant in a globalized world, where communication and travel reveal the simultaneity of opposing seasonal realities, such as summer holidays in one hemisphere coinciding with winter routines in the other. And this simultaneity highlights the role of Earth's tilt in creating diverse, yet complementary experiences across the planet. And from a scientific perspective, the hemispheric alternation of seasons provides a natural laboratory for studying climate processes, because it allows researchers to compare how similar mechanisms operate under opposite conditions, improving understanding of atmospheric dynamics, ocean circulation, and ecological response. In this comparative approach has deepened insight into how energy flows through Earth's systems, reinforcing the central role of axial tilt. And over geological timescales, the alternation of hemispheric seasons has influenced the evolution of landforms, soils, and ecosystems, because repeated cycles of warming and cooling drive processes such as erosion, sediment transport, and nutrient cycling, shaping landscapes in ways that reflect long-term seasonal rhythms. And these rhythms are encoded in geological records, such as tree rings, ice cores, and sediment layers, which preserve evidence of past seasonal patterns and allow reconstruction of Earth's climatic history. And the persistence of hemispheric alternation across millions of years demonstrates the durability of Earth's axial configuration, even as continents drift and climates shift. And this durability provides a stable framework within which change can occur without chaos. And when viewed from space, the seasonal contrast between hemispheres is visible in shifting patterns of vegetation, snow cover, and cloud formation, offering a visual testament to the power of tilt-driven orientation. And these global-scale changes unfold slowly enough to appear graceful, reinforcing the sense that Earth's motion is not hurried but deliberate. And by understanding that one hemisphere leans toward the sun while the other leans away, we gain a clearer picture of why seasons are complementary rather than universal, and why global balance emerges from opposition rather than uniformity. And this understanding invites reflection on the broader principle that stability often arises from alternating states rather than constant conditions. And in this way, Earth's seasonal system becomes not only a physical phenomenon, but also a model of balance, demonstrating how opposing experiences can coexist within a single, coherent whole. And as Earth continues its endless journey around the Sun, this hemispheric dance repeats with unwavering precision, ensuring that light, warmth, and energy are shared across the planet in turn, sustaining life through a rhythm of contrast, exchange, and renewal that has endured across deep time and will continue long into the future. When the northern hemisphere tilts toward the Sun, it experiences summer, while the southern hemisphere simultaneously experiences winter, and this elegant opposition lies at the heart of Earth's seasonal rhythm, demonstrating how a simple geometric orientation can generate profoundly different conditions on opposite sides of the planet. Because the hemisphere facing the Sun receives sunlight at higher angles and for longer durations, increasing energy input, warming land and water, and driving atmospheric and oceanic processes that reinforce summer conditions, while the opposite hemisphere, tilted away, receives sunlight at lower angles for shorter periods, reducing energy input, cooling surface temperatures, and creating winter conditions. And this simultaneous contrast ensures that Earth maintains a global balance in energy distribution, preventing extreme overheating or overcooling of the planet as a whole. And the phenomenon shapes a wide range of environmental, ecological, and human patterns, because the predictable alternation between summer and winter allows plants and animals to time reproduction, migration, growth, and dormancy in response to environmental cues that vary between hemispheres. And in humans, it has dictated the timing of agricultural cycles, social traditions, and cultural observances for millennia, embedding knowledge of Earth's orientation directly into survival strategies and communal planning. And the fixed axial tilt that produces this opposition also contributes to the gradual progression of seasons, because sunlight angles and day lengths change incrementally rather than abruptly, allowing ecosystems to adjust slowly and minimizing shock to life systems. And as the northern hemisphere leans more directly into sunlight, the lengthening of days and rising of the sun's path across the sky increases insolation, which in turn warms the atmosphere and triggers circulation patterns that drive summer weather, rainfall, and monsoon cycles. While at the same time, the southern hemisphere experiences contraction of daylight, lower solar angles, and cooling temperatures, which similarly influence winter weather, stabilizing climates through a predictable pattern of energy flow. And these opposing seasonal effects also manifest in large-scale geographic phenomena, because the contrast between hemispheres drives the formation of pressure systems and jet streams that circulate energy globally, linking local climate to planetary scale processes. And the alternation between summer and winter in opposite hemispheres ensures that while one hemisphere stores heat, the other releases it, maintaining equilibrium in oceans and atmosphere. And this heat transfer helps moderate extremes, preventing runaway warming or cooling while supporting life across latitudes. And the reversal of seasons between hemispheres is also evident in biological cycles, because while plants flourish in one region, they may be dormant in another. While migratory species exploit the seasonal contrast to move between regions, following favorable conditions from pole to pole, and this movement underscores the interdependence of hemispheric ecosystems, all orchestrated by the tilt of Earth's axis and the constancy of its orientation. And over long time scales, the reliability of this opposition has shaped evolutionary pressures, allowing species to develop adaptations that anticipate seasonal changes. H as hibernation, fat storage, and breeding cycles that are keyed precisely to temperature, daylight, and resource availability. And human societies have likewise structured calendars, festivals, and agricultural practices around the contrast of opposite hemispheric seasons, demonstrating a cultural recognition of the natural rhythm that transcends local experience. And the opposition of summer and winter also affects ice formation and melting. Because when one hemisphere experiences prolonged summer, polar ice retreats, allowing oceans to absorb heat, while the opposite hemisphere experiences winter, enabling ice accumulation and energy reflection, creating a dynamic but balanced system that regulates climate globally and at extreme latitudes. The effects of this hemispheric opposition are amplified, producing polar day and night that define extreme seasonal environments, while equatorial regions experience less variation but still feel the influence of seasonal energy shifts, highlighting the gradient of solar impact across latitudes. And this gradient is a direct consequence of the interplay between axial tilt and hemispheric orientation, producing both contrast and continuity in climate patterns. And the simultaneous summer-winter phenomenon also affects atmospheric chemistry, because solar intensity drives photochemical reactions that vary by hemisphere and season, influencing ozone formation, cloud patterns, and even precipitation chemistry, demonstrating that the tilt-driven opposition shapes not only temperature, but also the very composition of the atmosphere. And human perception and behavior are attuned to these alternating seasons, because cultural rituals, energy use, and daily routines often reflect the local seasonal context, while global awareness of opposite hemispheric conditions fosters a broader understanding of Earth systems, highlighting interconnectedness and the need to consider global energy balance rather than purely local experience. And the reliability of this hemispheric alternation is critical for long-term ecological stability, because predictable cycles allow species to plan and conserve energy across months, seasons, and years, creating resilience in ecosystems that could not survive under chaotic or irregular conditions. And this alternation also influences ocean circulation, because temperature contrasts between hemispheres drive differences in sea surface heating, evaporation, and pressure systems, which in turn guide currents such as the thermohaline circulation, redistributing heat and nutrients around the globe and linking local conditions to planetary-scale climate dynamics. And in human terms, the simultaneous summer-winter contrast informs global trade, agriculture, and migration patterns. Because when one hemisphere is in harvest season, prompting exchange and cooperation that depend on predictable seasonal timing, and this economic and social interconnection reinforces the value of understanding Earth's axial geometry, because the natural alternation of seasons underpins human planning and global coordination, and the contrast of opposite seasons also creates variation in vegetation, snow cover, and albedo, which feeds back into climate by reflecting or absorbing solar energy, stabilizing temperatures, and sustaining atmospheric circulation. And these feedbacks are strongest when one hemisphere is in full summer, while the other is in full winter, demonstrating the centrality of opposition in Earth's energy budget. And even the rhythm of celestial observation depends on this alternation, because astronomers notice changes in the night sky that correspond to local season, which occurs inversely in the opposite hemisphere, providing a natural clock that repeats annually yet varies spatially, reinforcing the predictability of the system. And in a broader perspective, the simultaneous experience of summer and winter across hemispheres illustrates how stability and variation coexist in Earth systems, because contrast creates balance, diversity, and resilience without disrupting overall coherence. And this principle resonates across scales, from global climate to ecosystem dynamics, human culture, and individual experience. And by observing that when the northern hemisphere tilts toward the sun, the southern hemisphere tilts away, we can appreciate the elegance of this natural design, in which simple geometry produces complex life-sustaining outcomes. And as Earth continues its steady orbit year after year, this hemispheric opposition repeats predictably, reminding us that the planet's rhythms are not arbitrary but arise from enduring cosmic relationships, and that the alternation of seasons between hemispheres is both a scientific fact and a profound expression of planetary harmony, sustaining ecosystems, guiding human activity, and creating a dynamic, interconnected world that balances energy, life, and time in a continuous, rhythmic cycle. The gradual change of seasons, driven by Earth's tilt and orbital motion, is one of the most elegant demonstrations of slow, continuous variation in nature, because as the planet progresses along its orbital path, the angle and duration of sunlight change incrementally, producing a smooth transition from one season to the next, rather than abrupt shifts. And this gradualism is critical for life, because organisms rely on predictable environmental cues to time reproduction, growth, migration, and dormancy. And abrupt or chaotic changes would disrupt these cycles, potentially threatening survival. And this slow progression is apparent in the subtle increases in day length after the winter solstice, which signal the approach of spring. And the gradually rising sun delivers progressively more energy each day, warming the land and atmosphere, and initiating biological responses, from budding plants to migratory birds returning from wintering grounds. And as Earth continues its orbit, the lengthening days reach their maximum at the summer solstice, when the sun's path is highest in the sky and daylight lasts the longest, and this extended exposure provides the energy necessary for peak photosynthetic activity, increased biological productivity, and elevated temperatures, which in turn influence atmospheric pressure, circulation and precipitation patterns, and the gradual decline of sunlight after the solstice signals the transition into autumn. As temperatures decrease, daylight shortens, and ecosystems begin to prepare for winter, storing energy, shedding leaves, and reducing metabolic activity. And this slow change provides a buffer against sudden environmental stress, allowing species to adapt incrementally rather than facing abrupt shocks. And the concept of gradualism also applies to human experience, because our cultural and agricultural systems have evolved to anticipate and respond to slow shifts in season, scheduling planting, harvesting, festivals and rituals in alignment with predictable patterns of light and temperature. And this alignment fosters social stability and continuity, reinforcing the importance of slow, cumulative change in both natural and human systems. And the incremental nature of seasonal progression is also reflected in temperature patterns, because thermal inertia in the land, oceans, and atmosphere means that the warmest and coldest days often lag behind the solstices, smoothing transitions and moderating extremes. And this delay allows energy absorbed during long summer days to accumulate gradually, warming the environment even as daylight begins to shorten, while in winter, accumulated heat slowly dissipates, preventing immediate drops in temperature and maintaining a more stable climate. And the gradual change of seasons also interacts with weather systems, because as the sun's angle and day length shift, pressure systems adjust, winds shift, and precipitation patterns respond, producing smooth yet complex variations in local and regional climate. And these variations, while subtle day to day, accumulate over weeks and months to produce the familiar progression from spring to summer, to autumn to winter, and the slow movement of the sun along the horizon, as seen from any given latitude, provides a visual confirmation of this gradual change, with sunrise and sunset points inching northward or southward each day, lengthening or shortening shadows, and altering the quality of light, which in turn affects both ecological processes and human perception. And this observable progression reinforces the underlying principle that small, consistent changes over time can produce meaningful outcomes, whether in climate, biology, or human activity. And from an ecological perspective, gradual seasonal change allows populations to synchronize life history events, because organisms measure not only temperature but also photoperiod, the length of daylight, as a primary cue for timing key events. And this cue remains reliable precisely because changes occur incrementally rather than unpredictably. And these predictable shifts have driven the evolution of sophisticated adaptive strategies, from flowering and leaf drop to migration and hibernation, which depend on the continuity of slow seasonal variation. And in humans, the gradual progression of seasons has shaped cultural narratives, calendars, and religious observances, because the predictable unfolding of time through incremental light and temperature change provides a natural framework for organizing work, celebration, and reflection. And this continuity has long been essential for agriculture, as farmers rely on the slow accumulation of warmth and the gradual lengthening of days to determine planting and harvesting times. Aligning human activity with planetary rhythms and the principle of gradualism extends to climate feedbacks, because slowly changing temperatures influence the melting and accumulation of snow and ice, the distribution of energy across land and ocean, and the strength and position of atmospheric circulation systems, all of which evolve incrementally rather than instantaneously, reinforcing stability and predictability. And at high latitudes, gradual change is especially critical, because the extreme variation in day length between summer and winter would otherwise be more disruptive if shifts occurred abruptly. And instead, the steady progression allows organisms and human societies to anticipate conditions, store resources, and plan activities in alignment with slowly unfolding environmental patterns. And this gradualism is mirrored in the ocean, where currents and temperature gradients respond slowly to seasonal changes, distributing heat and moderating climate across hemispheres. And in turn, these oceanic responses feed back into the atmosphere, further smoothing seasonal variation. And this interconnectedness demonstrates how slow, continuous processes propagate through multiple components of the Earth system, creating coherence and resilience. And the incremental nature of seasonal change also shapes light quality, because as the sun's angle gradually shifts, the color of sunlight, the length of shadows, and the intensity of radiation change in subtle ways, producing familiar patterns of warmth, coolness, and atmospheric scattering that have both ecological and aesthetic effects. And humans, attuned to these changes, experience the gradual unfolding of the seasons through sight, temperature, and the rhythms of day and night. And this slow, observable progression fosters psychological and emotional stability, because change is neither abrupt nor overwhelming, but steady and comprehensible. And from a planetary perspective, the incremental nature of seasons highlights the importance of geometric relationships and orbital mechanics, because small daily changes in position relative to the sun translate over time into large-scale environmental variation. And this amplification of subtle shifts into meaningful outcomes exemplifies how cumulative processes shape planetary experience. And over geological time, slow changes in tilt, precession, and orbital eccentricity modulate the intensity and timing of seasonal change, creating long-term climate cycles that influence ice ages and interglacial periods. Yet these cycles operate within the broader context of consistent, gradual annual change, providing a stable framework upon which evolutionary and cultural processes can build. And the concept of gradualism also teaches a broader lesson about time and process, because it demonstrates that meaningful transformations, whether ecological, climatic, or social, rarely occur instantaneously, but instead accumulate slowly through small, persistent changes that maintain coherence while allowing diversity and adaptation. And this perspective encourages patience, planning, and trust in steady processes, showing that stability and progress emerge not from sudden shifts, but from the careful orchestration of incremental variation. And ultimately, the gradual change of seasons serves as a living example of how small underscores the interdependence of hemispheric ecosystems, all orchestrated by the tilt of Earth's axis and the constancy of its orientation. And over long time scales, the reliability of this opposition has shaped evolutionary pressures, allowing species to develop adaptations that anticipate seasonal changes, such as hibernation, fat storage, and breeding cycles that are keyed precisely to temperature, daylight, and resource availability. And human societies have likewise structured calendars, festivals, and agricultural practices around the contrast of opposite hemispheric seasons, demonstrating a cultural recognition of the natural rhythm that transcends local experience. And the opposition of summer and winter also affects ice formation and melting. Because when one hemisphere experiences prolonged summer, polar ice retreats, allowing oceans to absorb heat, while the opposite hemisphere experiences winter, enabling ice accumulation and energy reflection, creating a dynamic but balanced system that regulates climate globally. And at extreme latitudes, the effects of this hemispheric opposition are amplified, producing polar day and night that define extreme seasonal environments, while equatorial regions experience less variation but still feel the influence of seasonal energy shifts, highlighting the gradient of solar impact across latitudes. And this gradient is a direct consequence of the interplay between axial tilt and hemispheric orientation, producing both contrast and continuity in climate patterns. And the simultaneous summer-winter phenomenon also affects atmospheric chemistry, because solar intensity drives photochemical reactions that vary by hemisphere and season, influencing ozone formation, cloud patterns, and even precipitation chemistry, demonstrating that the tilt-driven opposition shapes not only temperature, but also the very composition of the atmosphere. And human perception and behavior are attuned to these alternating seasons, because cultural rituals, energy use, and daily routines often reflect the local seasonal context, while global awareness of opposite hemispheric conditions fosters a broader understanding of Earth's systems, highlighting interconnectedness and the need to consider global energy balance rather than purely local experience. And the reliability of this hemispheric alternation is critical for long-term ecological stability, because predictable cycles allow species to plan and conserve energy across months, seasons, and years, creating resilience in ecosystems that could not survive under chaotic or irregular conditions. And this alternation also influences ocean circulation, because temperature contrasts between hemispheres drive differences in sea surface heating, evaporation, and pressure systems, which in turn guide currents such as the thermohaline circulation, redistributing heat and nutrients around the globe and linking local conditions to planetary-scale climate dynamics. And in human terms, the simultaneous summer-winter contrast informs global trade, agriculture, and migration patterns, because when one hemisphere is in harvest season, the other is in winter scarcity, prompting exchange and cooperation that depend on predictable seasonal timing. And this economic and social interconnection reinforces the value of understanding Earth's axial geometry, because the natural alternation of seasons underpins human planning and global coordination. And the contrast of opposite seasons also creates variation in vegetation, snow cover, and albedo, which feeds back into climate by reflecting or absorbing solar energy, stabilizing temperatures, and sustaining atmospheric circulation. And these feedbacks are strongest when one hemisphere is in full summer, while the other is in full winter, demonstrating the centrality of opposition in Earth's energy budget. And even the rhythm of celestial observation depends on this alternation, because astronomers notice changes in the night sky that correspond to local season, which occurs inversely in the opposite hemisphere, providing a natural clock that repeats annually, yet varies spatially, reinforcing the predictability of the system. And in a broader perspective, the simultaneous experience of summer and winter across hemispheres illustrates how stability and variation coexist in Earth systems, because contrast creates balance, diversity, and resilience without disrupting overall coherence. And this principle resonates across scales, from global climate to ecosystem dynamics, human culture, and individual experience. And by observing that when the northern hemisphere tilts toward the sun, the southern hemisphere tilts away, we can appreciate the elegance of this natural design, in which simple geometry produces complex, life-sustaining outcomes. And as Earth continues its steady orbit year after year, this hemispheric opposition repeats predictably, reminding us that the planet's rhythms are not arbitrary but arise from enduring cosmic relationships, and that the alternation of seasons between hemispheres is both a scientific fact and a profound expression of planetary harmony, sustaining ecosystems, guiding human activity, and creating a dynamic, interconnected world that balances energy, life, and time in a continuous rhythmic cycle. The gradual change of seasons, driven by Earth's tilt and orbital motion, is one of the most elegant demonstrations of slow, continuous variation in nature, because as the planet progresses along its orbital path, the angle and duration of sunlight change incrementally, producing a smooth transition from one season to the next rather than abrupt shifts. And this gradualism is critical for life, because organisms rely on predictable environmental cues to time reproduction, growth, migration, and dormancy. And abrupt or chaotic changes would disrupt these cycles, potentially threatening survival. And this slow progression is apparent in the subtle increases in day length after the winter solstice, which signal the approach of spring. And the gradually rising sun delivers progressively more energy each day, warming the land and atmosphere, and initiating biological responses, from budding plants to migratory birds returning from wintering grounds. And as Earth continues its orbit, the lengthening days reach their maximum at the summer solstice, when the sun's path is highest in the sky and daylight lasts the longest. And this extended exposure provides the energy necessary for peak photosynthetic activity, increased biological productivity, and elevated temperatures, which in turn influence atmospheric pressure, circulation and precipitation patterns, and the gradual decline of sunlight after the solstice signals the transition into autumn. As temperatures decrease, daylight shortens, and ecosystems begin to prepare for winter, storing energy, shedding leaves, and reducing metabolic activity. And this slow change provides a buffer against sudden environmental stress, allowing species to adapt incrementally rather than facing abrupt shocks. And the concept of gradualism also applies to human experience, because our cultural and agricultural systems have evolved to anticipate and respond to slow shifts in season, scheduling planting, harvesting, festivals, and rituals in alignment with predictable patterns of light and temperature. And this alignment fosters social stability and continuity, reinforcing the importance of slow, cumulative change in both natural and human systems. And the incremental nature of seasonal progression is also reflected in temperature patterns, because thermal inertia in the land, oceans, and atmosphere means that the warmest and coldest days often lag behind the solstices, smoothing transitions and moderating extremes. And this delay allows energy absorbed during long summer days to accumulate gradually, warming the environment even as daylight begins to shorten, while in winter, accumulated heat slowly dissipates, preventing immediate drops in temperature and maintaining a more stable climate. And the gradual change of seasons also interacts with weather systems, because as the sun's angle and day length shift, pressure systems adjust, winds shift, and precipitation patterns respond, producing smooth yet complex variations in local and regional climate. And these variations, while subtle day to day, accumulate over weeks and months to produce the familiar progression from spring to summer, to autumn to winter. And the slow movement of the sun along the horizon, as seen from any given latitude, provides a visual confirmation of this gradual change, with sunrise and sunset points inching northward or southward each day, lengthening or shortening shadows, and altering the quality of light, which in turn affects both ecological processes and human perception. And this observable progression reinforces the underlying principle that small, consistent changes over time can produce meaningful outcomes, whether in climate, biology, or human activity. And from an ecological perspective, gradual seasonal change allows populations to synchronize life history events, because organisms measure not only temperature but also photoperiod, the length of daylight as a primary cue for timing key events. And this cue remains reliable precisely because changes occur incrementally rather than unpredictably. And these predictable shifts have driven the evolution of sophisticated adaptive strategies, from flowering and leaf drop to migration and hibernation, which depend on the continuity of slow seasonal variation. And in humans, the gradual progression of seasons has shaped cultural narratives, calendars, and religious observances. Because the predictable unfolding of time through incremental light and temperature change provides a natural framework for organizing work, celebration, and reflection. And this continuity has long been essential for agriculture, as farmers rely on the slow accumulation of warmth and the gradual lengthening of days to determine planting and harvesting times, aligning human activity with planetary rhythms. And the principle of gradualism extends to climate feedbacks, because slowly changing temperatures influence the melting and accumulation of snow and ice, the distribution of energy across land and ocean, and the strength and position of atmospheric circulation systems, all of which evolve incrementally rather than instantaneously, reinforcing stability and predictability. And at high latitudes, gradual change is especially critical, because the extreme variation in day length between summer and winter would otherwise be more disruptive if shifts occurred abruptly. And instead, the steady progression allows organisms and human societies to anticipate conditions, store resources, and plan activity in alignment with slowly unfolding environmental patterns. And this gradualism is mirrored in the ocean, where currents and temperature gradients respond slowly to seasonal changes, distributing heat and moderating climate across hemispheres. And in turn, these oceanic responses feed back into the atmosphere, further smoothing seasonal variation. And this interconnectedness demonstrates how slow, continuous processes propagate through multiple components of the Earth system, creating coherence and resilience. And the incremental nature of seasonal change also shapes light quality, because as the sun's angle gradually shifts, the color of sunlight, the length of shadows, and the intensity of radiation change in subtle ways, producing familiar patterns of warmth, coolness, and atmospheric scattering that have both ecological and aesthetic effects. And humans, attuned to these changes, experience the gradual unfolding of the seasons through sight, temperature, and the rhythms of day and night. And this slow, observable progression fosters psychological and emotional stability, because change is neither abrupt nor overwhelming, but steady and comprehensible. And from a planetary perspective, the incremental nature of seasons highlights the importance of geometric relationships and orbital mechanics, because small daily changes in position relative to the sun translate over time into large-scale environmental variation, and this amplification of subtle shifts into meaningful outcomes exemplifies how cumulative processes shape planetary experience. And over geological time, slow changes in tilt, precession, and orbital eccentricity modulate the intensity and timing of seasonal change, creating long-term climate cycles that influence ice ages and interglacial periods. Yet these cycles operate within the broader context of consistent, gradual annual change, providing a stable framework upon which evolutionary and cultural processes can build. And the concept of gradualism also teaches a broader lesson about time and process, because it demonstrates that meaningful transformations, whether ecological, climatic, or social, rarely occur instantaneously, but instead accumulate slowly through small, persistent changes that maintain coherence while allowing diversity and adaptation. And this perspective encourages patience, planning, and trust in steady processes, showing that stability and progress emerge not from sudden shifts, but from the careful orchestration of incremental variation. And ultimately, the gradual change of seasons serves as a living example of how small, predictable motions within the solar system translate into rich, continuous rhythms that govern life, climate, and human experience, a rhythm that repeats year after year, offering continuity, predictability, and a subtle but profound structure upon which the myriad processes of the planet unfold in harmony. The axial tilt of Earth, combined with its orbital motion, creates not only gradual seasonal change, but also a distinct variation in solar intensity at different latitudes. And this differential heating is a critical driver of climate patterns, because sunlight striking the equator arrives at a steeper angle, concentrating energy over a smaller surface area, while the same sunlight reaches higher latitudes at a shallower angle, spreading energy over a larger area and reducing heating efficiency. And this simple geometric principle explains why tropical regions remain warm year-round, while temperate and polar regions experience more pronounced seasonal swings. And the tilt amplifies these effects by modulating the sun's height in the sky and the duration of daylight throughout the year, so that even small changes in orientation translate into measurable differences in energy received at each latitude. And as Earth progresses through its orbit, the tilt ensures that mid-latitude regions experience significant seasonal contrasts, with higher solar angles and longer days producing summer warmth, and lower solar angles and shorter days producing winter cold. And this contrast is further reinforced by the combination of land and ocean distribution, because land heats and cools more quickly than water, accentuating seasonal temperature extremes in continental interiors, while oceans moderate conditions in coastal areas. And these latitudinal differences in solar intensity also drive the formation of pressure systems and wind patterns, because differential heating causes air to rise in warmer regions and sink in cooler regions, generating circulation cells such as the Hadley, Ferrel, and polar cells, which distribute heat and moisture around the planet, linking regional seasons to global climate dynamics. And the interplay of axial tilt and latitude also influences the timing and intensity of precipitation, because solar energy drives evaporation, cloud formation, and convection, and the seasonal shift in solar intensity modulates these processes in predictable ways, creating wet and dry periods that are critical for ecosystems, agriculture, and human society. And this predictable pattern allows organisms to synchronize reproduction, migration, and growth with periods of abundance, and ensures that human agricultural practices align with periods of maximum sunlight and rainfall, creating a direct connection between cosmic geometry and terrestrial survival. And at extreme latitudes, the variation in solar intensity becomes even more pronounced, producing phenomena such as the midnight sun during summer and polar night during winter, which in turn influence temperature, wind, and ice cover, creating environments that challenge life to adapt to extremes while still operating within the broader rhythm of gradual seasonal change. And this latitudinal gradient in solar energy also affects oceanic processes, because higher energy input in equatorial regions warms surface waters, driving currents such as the equatorial gyres, and contributing to the global thermohaline circulation, which transports heat toward the poles and moderates seasonal extremes. And these oceanic processes interact with atmospheric dynamics to create monsoons, trade winds, and jet streams, all of which respond to the differential heating produced by axial tilt and latitude. And this complex web of interactions illustrates how a single planetary parameter, tilt, propagates its influence through multiple systems, shaping climate, ecosystems, and human activity simultaneously. And the variation in solar intensity also drives phenological cycles, because many species rely on the timing and amount of sunlight to initiate flowering, leaf growth, migration, or reproduction. And this timing is closely linked to latitude, because organisms at higher latitudes must respond to larger swings in solar input, while those near the equator experience more subtle seasonal cues. And this latitudinal variation in biological response highlights the adaptive significance of tilt-driven solar variation. And over evolutionary time, species have evolved mechanisms to anticipate and exploit these differences, ensuring survival and reproductive success across diverse environments. And the variation in solar intensity with latitude also has profound implications for human society, because it influences energy demand, building design, and urban planning, as well as agricultural practices, social customs, and cultural attitudes toward light and warmth. And the predictability of this variation allows societies to plan and coordinate activities in alignment with environmental rhythms, fostering stability and resilience. And beyond practical applications, the variation in solar intensity creates aesthetic and perceptual effects, because the quality and color of sunlight change with angle and duration, producing subtle differences in shadow length, atmospheric scattering, and the intensity of illumination, which in turn affect mood, behavior, and the human experience of space and time. And this perceptual dimension reinforces the connection between cosmic mechanics and daily life, reminding us that large-scale astronomical geometry shapes both physical conditions and subjective experience. And the interplay of tilt, latitude, and solar intensity also governs snow cover, ice formation, and glacial dynamics, because higher latitudes experience lower solar energy, which allows ice to accumulate during winter, while lower latitudes remain relatively ice-free, and this latitudinal contrast contributes to Earth's energy balance, because reflective ice surfaces return solar energy to space, while dark oceans absorb it, moderating global climate. And the gradual variation in solar intensity also influences the timing of seasonal weather events, because the buildup of heat and differential warming between regions sets the stage for storms, monsoons, and other dynamic phenomena. And this predictability allows humans to anticipate extreme events, plan agriculture, and prepare for environmental hazards, reinforcing the practical significance of axial tilt and latitudinal variation. And over geological time, small shifts in tilt and orbit modulate these latitudinal energy patterns, producing long-term climate cycles such as glacial and interglacial periods. Yet the fundamental pattern of differential heating with latitude remains, providing continuity for life to adapt and evolve. And by observing how solar intensity varies from equator to pole, and how this variation is amplified and moderated by tilt, day length, and orbital position, we gain a comprehensive understanding of how seasons are physically generated, how ecosystems respond, and how human societies are shaped by predictable patterns of energy input. And this understanding highlights the elegance of planetary mechanics, because a single constant tilt creates a dynamic, interconnected system of light, temperature, and seasonal rhythm, sustaining life and shaping climate across latitudes. And the predictable variation in solar intensity with latitude also provides a framework for scientific modeling, because it establishes a baseline against which other factors, such as ocean currents, topography, and atmospheric composition, can be analyzed. And these models allow prediction of weather, climate change, and ecological response, demonstrating how fundamental geometric relationships translate into practical knowledge. And the differential heating across latitudes also explains why equatorial regions have more stable climates, while higher latitudes experience greater seasonal extremes, a distinction that underpins agricultural planning, urban design, and environmental management. And this differential heating also creates seasonal migration patterns in the atmosphere and oceans, reinforcing the interconnectedness of global climate systems. And by studying these processes, scientists can trace the propagation of energy from sunlight to wind, water, and ecosystems, revealing a continuous chain of causality, originating in Earth's axial tilt and orbit, and ultimately, the variation in solar intensity with latitude, driven by tilt, represents one of the clearest and most fundamental expressions of planetary mechanics, because it converts abstract orientation into tangible differences in energy, life, and climate, shaping the rhythm of seasons, the flow of currents, the behavior of organisms, and the structure of human society in a precise, predictable, and elegant system that operates continuously across the globe year after year. Earth's seasons would be far more extreme and potentially chaotic without the stabilizing influence of the moon. Because while axial tilt is the primary driver of seasonal variation, the long-term stability of that tilt depends on gravitational interactions that prevent large, rapid shifts, and the moon plays a crucial role in this process by acting as a gravitational anchor that dampens wobble in Earth's rotational axis, ensuring that the tilt remains within a relatively narrow range over long periods of time. And the stabilization is essential because even small changes in axial tilt can significantly alter the distribution of sunlight across the planet, intensifying or weakening seasons in ways that would challenge ecosystems and climate systems. And without the moon's influence, Earth's axis would be more susceptible to gravitational perturbations from other planets, particularly massive neighbors like Jupiter, which could induce chaotic variations in tilt, potentially swinging it through wide angles over geological timescales. And such swings would produce extreme climatic shifts, with some periods experiencing intense seasonal contrasts, and others experiencing minimal variation, disrupting the predictable cycles that life depends upon. And the moon's stabilizing effect works by increasing Earth's rotational inertia, making it harder for external gravitational forces to significantly alter the axis orientation. And this increased stability ensures that Earth's tilt has remained close to its current value for millions of years, allowing the seasonal system to persist with remarkable consistency. And this consistency has been a foundational condition for the evolution of complex life, because organisms rely on long-term environmental predictability to develop specialized adaptations, such as seasonal reproduction, migration, and dormancy, which would be far more difficult under rapidly changing seasonal regimes. And the moon's role in stabilizing tilt also interacts with other long-term motions, such as axial precession, which causes the orientation of the axis to trace a slow circular path over tens of thousands of years. Yet this motion is gradual and predictable, ensuring that while the timing of seasons relative to Earth's orbital position may shift slightly, the overall structure of seasonal variation remains intact. And this gradual modulation contributes to long-term climate cycles, without undermining the basic rhythm of seasons. And from a climatic perspective, the moon's stabilizing influence supports the persistence of moderate seasonal contrasts that allow both polar ice and temperate ecosystems to coexist, preventing extreme oscillations that could lead to runaway glaciation or overheating. And this moderation has been critical in maintaining Earth's habitability across deep time. And when comparing Earth to other planets, the importance of lunar stabilization becomes even clearer, because planets with little or no large moon, such as Mars, experience greater variations in axial tilt over time, leading to more extreme and less predictable seasonal changes that have influenced their climatic and geological evolution. And while Mars still has seasons, its tilt has varied significantly, contributing to dramatic shifts in climate and ice distribution that challenge long-term stability. And this comparison highlights how Earth's relatively large moon has played a quiet but essential role in shaping the planet's environmental history. And beyond climate, the moon's influence on axial stability also affects ocean tides, which in turn interact with sea zonal cycles to influence coastal ecosystems, nutrient mixing, and biological rhythms, creating layered patterns of environmental variation that operate across daily, monthly, and annual timescales. And this layering adds richness and complexity to Earth's systems while preserving overall coherence. And the presence of the moon also affects Earth's rotation rate, gradually slowing it over billions of years, which has lengthened days and influenced the development of circadian rhythms, further embedding astronomical relationships into biological function. And this interplay between rotation, tilt, and orbit demonstrates how multiple celestial factors combine to produce the conditions we experience as seasons. And from a human perspective, the stability provided by the moon has enabled the development of reliable calendars, agricultural practices, and cultural traditions tied to seasonal cycles. Because without long-term predictability, planning and continuity would be far more difficult. And the moon itself has become a cultural symbol closely associated with timekeeping and seasonal awareness, reflecting an intuitive recognition of its role in shaping Earth's rhythms. And the stabilizing effect of the moon also contributes to the predictability of long-term climate patterns, allowing scientists to reconstruct past climates and anticipate future trends with greater confidence, because the fundamental parameters governing seasonal variation remain relatively constant. And this confidence supports informed decision-making in areas such as agriculture, resource management, and climate adaptation. And the moon's influence illustrates a broader principle in planetary science, namely that habitability often depends not on a single factor, but on the interaction of multiple elements that together create stability. And Earth's seasons emerge not solely from tilt or orbit, but from the combined effects of axial orientation, orbital motion, rotational dynamics, and gravitational relationships, all of which are subtly interconnected, and this interconnectedness underscores the fragility and resilience of planetary systems, because small changes in one component can have far-reaching consequences, yet when balanced appropriately, they can sustain life over immense timescales. And the moon's stabilizing role also invites reflection on contingency, because Earth's current seasonal system depends on historical events, such as the moon's formation, that could have unfolded differently, suggesting that the conditions supporting life are the product of both physical laws and cosmic history. And this realization deepens appreciation for the uniqueness of Earth's environment, while also guiding the search for habitable worlds elsewhere, as scientists look for planets with stabilizing factors that could support long-term climatic consistency. And in this context, Earth's seasons can be seen as the outcome of a finely tuned interplay between motion and restraint, where tilt creates variation, and the moon ensures that variation remains within life-supporting bounds, and this balance produces a seasonal rhythm that is dynamic, yet stable, diverse yet predictable, and capable of sustaining ecosystems, cultures, and civilizations across generations. And as Earth continues its journey around the sun, the moon continues its silent partnership, maintaining the orientation that allows seasons to unfold reliably, reminding us that even distant celestial bodies can exert profound influence on daily life, and that the rhythms we experience are the result of deep cosmic relationships operating quietly and persistently over time, shaping the environment in which life thrives, adapts, and endures. The winter solstice represents the moment in Earth's annual journey around the sun, when a given hemisphere is tilted most strongly away from incoming sunlight, producing the shortest day and longest night of the year, and this event arises directly from the geometry of Earth's axial tilt, rather than any sudden change in motion or distance, because Earth continues to rotate and orbit smoothly, while the orientation of its axis determines how sunlight is distributed across the planet. And at the winter solstice, the sun follows its lowest and shortest arc across the sky for that hemisphere, remaining close to the horizon even at midday and delivering sunlight at a shallow angle that spreads energy thinly over a larger surface area, reducing heating efficiency and leading to colder conditions. And this reduced solar exposure affects not only temperature but also atmospheric behavior, because less solar energy means weaker convection, lower evaporation rates, and changes in pressure systems that influence wind patterns and precipitation. And the shortening of daylight has profound biological consequences, as plants receive less light for photosynthesis, slowing growth or triggering dormancy, while animals respond to reduced daylight by conserving energy, migrating, hibernating, or altering behavior to survive colder and darker conditions. And humans, long before modern science, recognized the significance of this moment, marking it with monuments, rituals, and calendars because it symbolized both the depth of winter and the turning point after which daylight would gradually return. And although the winter solstice marks the minimum daylight, it does not immediately produce the coldest temperatures because Earth's surface and oceans store heat and release it slowly, creating a lag between minimum sunlight and minimum temperature. Yet the solstice sets the stage for the coldest period by limiting incoming energy. And at high latitudes this effect becomes extreme, with regions near the Arctic Circle experiencing very brief daylight or complete darkness, while regions closer to the equator experience a milder reduction in day length, demonstrating how latitude modulates the impact of the solstice. and the precise timing of the winter solstice varies slightly from year to year due to the details of Earth's orbit and calendar system, but its physical meaning remains constant, representing the point of maximum tilt away from the sun. And from a planetary perspective, the winter solstice illustrates how a fixed axial tilt transforms steady orbital motion into seasonal contrast, converting geometry into climate, light into darkness, and astronomical alignment into lived experience. And this predictable recurrence has allowed ecosystems and civilizations to synchronize their rhythms with the planet's motion, embedding the solstice deeply into natural cycles and cultural memory. And even in the modern world, with artificial lighting and climate control, the winter solstice continues to influence human mood, energy use, and biological rhythms, reminding us that the shortest day of the year is not merely an astronomical marker but a fundamental expression of how Earth's orientation governs light, heat, life, and time itself. Between the contrasting extremes of the solstices lie the equinoxes, two pivotal moments each year when day and night are nearly equal in length across the entire planet. And these events occur because Earth's axis, while still tilted, is oriented sideways relative to the sun, allowing sunlight to fall evenly across both hemispheres, rather than favoring one over the other. And during an equinox, the sun appears to rise due east and set due west. For almost all locations on Earth, tracing a balanced arc across the sky that symbolizes equilibrium between light and darkness. And this balance is not mere lie symbolic but physical, because the division of solar energy between hemispheres becomes nearly symmetrical, temporarily halting the progressive lengthening or shortening of days that dominates the periods before and after. And as a result, the equinoxes serve as transition points in the seasonal cycle, marking the shift from winter toward summer during the spring equinox, and from summer toward winter during the autumn equinox. And although day and night are described as equal, subtle variations still exist due to atmospheric refraction and the finite size of the sun's disk. Yet the concept of balance remains accurate enough to have guided calendars, agriculture, and cultural traditions for thousands of years. And from a climatic perspective, the equinoxes represent moments when solar heating is redistributed more evenly across latitudes, reducing the hemispheric imbalance that drives extreme seasonal contrasts. And this redistribution influences atmospheric circulation, because pressure gradients shift as heating patterns change, altering wind systems, storm tracks, and precipitation zones. And in many regions, the equinoxes are associated with dynamic weather, as the atmosphere adjusts from one dominant seasonal regime to another, producing variable conditions that can include storms, changing winds, and rapid temperature fluctuations. And these transitions are especially noticeable in temperate regions, where the equinoxes often coincide with visible ecological changes, such as budding plants and returning wildlife in spring, or leaf color changes, and harvest activity in autumn. And biologically, the equinoxes are powerful signals because many organisms are finely tuned to changes in daylight length, using photoperiod as a reliable cue to initiate growth, reproduction, migration, or dormancy. And the near equal day and night during equinoxes represents a threshold point that can trigger cascading biological responses across ecosystems. And for plants, increasing daylight after the spring equinox stimulates photosynthesis and growth, while decreasing daylight after the autumn equinox signals the approach of dormancy and resource conservation. And animals respond in parallel, adjusting behavior and physiology in anticipation of upcoming seasonal conditions, rather than reacting only to immediate temperature changes. And this anticipatory response highlights the importance of predictable astronomical cues in maintaining ecological stability. And human civilizations have long recognized the significance of the equinoxes, embedding them into agricultural calendars, religious observances, and architectural alignments, because they provided reliable markers for planting, harvesting, and seasonal planning. And ancient monuments around the world were constructed to align with equinox sunrises or sunsets. reflecting a deep awareness of Earth's geometry and its influence on life. And even today, modern calendars, school years, and economic cycles often align loosely with equinox timing, demonstrating the persistence of these ancient rhythms in contemporary society. And from a global perspective, the equinoxes emphasize Earth's interconnectedness because they are experienced simultaneously worldwide, linking diverse cultures and environments through a shared astronomical event. And this simultaneity reinforces the idea that seasons are not isolated local phenomena, but expressions of a planetary system operating as a whole. And the equinoxes also play a crucial role in defining climate zones, because they mark the moments when the sun crosses the celestial equator, shifting the region of maximum solar heating northward or southward, and driving the seasonal migration of weather systems, such as the intertropical convergence zone, monsoons, and jet streams. And these large-scale shifts influence rainfall patterns, drought cycles, and storm development, affecting billions of people in countless ecosystems. And in the oceans, the equinox-driven redistribution of solar energy influences surface temperatures and currents, contributing to seasonal changes in marine productivity and nutrient mixing. And this demonstrates how a seemingly simple alignment of Earth and Sun can propagate through complex systems, shaping conditions on land, sea, and air. And psychologically and culturally, the equinoxes often symbolize balance, renewal, or transition, reflecting the human tendency to mirror natural rhythms in meaning-making and ritual. And this symbolism persists because the physical reality of equal light and darkness resonates deeply with human perception and experience, especially after long periods dominated by either increasing or decreasing daylight. And scientifically, the equinoxes provide valuable reference points for understanding Earth's motion, because they define the boundaries between astronomical seasons and serve as anchors for measuring orbital dynamics, axial orientation, and long-term climate trends. And by studying how conditions change before and after equinoxes, scientists gain insight into the responsiveness of Earth's systems to shifting solar input, including the lagged responses of temperature, ice cover, and biological activity. And over geological timescales, the timing and intensity of equinox-related effects had been influenced by subtle variations in Earth's orbit and tilt, contributing to long-term climate patterns without disrupting the fundamental structure of the seasonal cycle. And this persistence highlights the robustness of Earth's seasonal framework, which has endured across ice ages, continental drift, and evolutionary change. And ultimately, the equinoxes represent moments of planetary balance embedded within a cycle of contrast, reminding us that Earth's seasons are not defined solely by extremes, but by transitions that allow systems to adjust, prepare, and respond gradually. And this balance between change and continuity is what makes the seasonal cycle both dynamic and stable, supporting life, culture, and climate across the planet, year after year, in a rhythm that is as precise as it is enduring. During the equinoxes, Earth's axis is oriented sideways relative to the Sun, a geometric alignment that produces one of the most balanced moments in the planet's annual cycle. Because although Earth's axis remains tilted at approximately 23.5 degrees relative to its orbital plane, the direction of that tilt is neither toward nor away from the Sun at these times, allowing sunlight to be distributed more evenly between the northern and southern hemispheres. And this sideways orientation means that the Sun's rays strike the equator more directly, while both hemispheres receive comparable angles and durations of sunlight, resulting in nearly equal lengths of day and night worldwide. And this balance emerges not from any pause or change in Earth's motion, but from the continuous progression of Earth along its orbit, which gradually changes the orientation of the tilted axis relative to the Sun over the course of the year. And at the equinoxes, the Sun appears to cross the celestial equator, marking a transition in the apparent solar path that has been carefully observed and recorded by astronomers for millennia. And from a physical perspective, the even distribution of sunlight reduces hemispheric contrasts in heating, temporarily weakening the energy imbalance that drives strong seasonal extremes. And this redistribution affects atmospheric circulation because temperature differences between hemispheres help power large-scale wind systems. So when those differences diminish, the atmosphere enters a transitional state characterized by shifting pressure patterns and variable weather. And this is why equinox periods are often associated with dynamic and sometimes unstable conditions, as the climate system adjusts to the changing balance of solar input. And in the oceans, the more symmetrical heating pattern influences surface temperatures and currents, contributing to seasonal transitions in marine ecosystems and productivity. And biologically, the sideways tilt during equinoxes creates a critical signaling moment, because many organisms are sensitive not only to temperature but also to day length. And the equinox represents a threshold where the trend in daylight reverses direction, either increasing after the spring equinox or decreasing after the autumn equinox. And plants respond to these changes by activating or suppressing growth processes, while animals adjust behavior related to breeding, migration, and energy storage. And these responses are anticipatory rather than reactive, allowing ecosystems to prepare for upcoming seasonal conditions rather than merely responding after changes occur. And this anticipatory nature underscores the importance of predictable astronomical cues in maintaining ecological stability. And for human societies, the equinoxes have historically been moments of profound significance because they provided reliable markers for seasonal planning, agricultural scheduling, and ceremonial observance. And ancient cultures around the world built monuments and observatories aligned with equinox sunrises or sunsets, demonstrating a sophisticated understanding of Earth's axial geometry and its relationship to the sun. And these alignments were not merely symbolic, but practical, enabling communities to track time and anticipate seasonal changes essential for survival. And, from a modern scientific standpoint, the equinoxes serve as reference points for defining astronomical seasons and for calibrating measurements of Earth's orbit, rotation, and axial orientation. And satellites and observatories continue to use these moments to refine models of Earth's motion and climate behavior. And the sideways tilt during equinoxes also highlights the elegance of Earth's seasonal mechanism, because it shows that profound environmental changes can arise from orientation alone rather than changes in speed, distance, or energy output. And this principle extends to planetary science more broadly, offering insight into how seasons might operate on other worlds with different tilts and orbital characteristics. And by comparing Earth's equinox behavior to that of other planets, scientists gain perspective on why Earth's seasonal system is relatively moderate and stable, supporting a wide range of life. And philosophically, the equinoxes embody the concept of balance, embedded within motion, illustrating how a constantly moving system can pass through moments of symmetry without ever stopping or repeating exactly the same configuration. And this dynamic balance resonates with human experience, where periods of transition often feel both unstable and full of potential, and even in contemporary life, largely insulated from direct dependence on natural cycles, the equinoxes still influence energy use, mood, and social rhythms, as changing daylight subtly affects sleep patterns, activity levels, and psychological well-being. And scientifically, the sideways orientation of Earth's axis during equinoxes provides a clear demonstration of how axial tilt operates as a three-dimensional phenomenon, not simply a static angle but a directional vector, whose relationship to the sun changes continuously. And understanding this relationship helps clarify common misconceptions about seasons, reinforcing the idea that it is the angle and duration of sunlight, rather than proximity to the sun, that governs seasonal variation. And over long time scales, the equinox positions themselves shift slightly due to precession and other orbital cycles, yet their fundamental role as moments of balanced illumination remains unchanged, highlighting the resilience of Earth's seasonal framework. And ultimately, the equinoxes, defined by Earth's sideways tilt relative to the sun, represent moments when the planet briefly shares sunlight equally across hemispheres, offering a pause between extremes and a reminder that Earth's seasons are shaped by geometry, motion, and balance working together in a precise and enduring rhythm. Earth's orbit around the Sun is slightly elliptical rather than perfectly circular, a subtle but important characteristic that shapes how our planet moves through space and time. Because instead of maintaining a constant distance from the Sun, Earth follows an oval-shaped path, in which the Sun is positioned slightly off-center, and this geometry arises naturally from the gravitational interaction between Earth and the Sun as described by the laws of orbital mechanics, particularly those first formalized by Johannes Kepler, who demonstrated that planetary orbits are ellipses rather than circles, and in Earth's case, this ellipse is very close to circular, with only a small difference between the closest and farthest points in its orbit. Yet this small deviation is enough to influence orbital speed, timing, and long-term climate behavior without dominating seasonal change. And as Earth travels along this elliptical path, it moves slightly faster when it is closer to the Sun and slightly slower when it is farther away, conserving angular momentum while maintaining a stable orbit. And this variation in speed means that the length of astronomical seasons is not perfectly equal, with some seasons lasting a few days longer than others, depending on where they fall along the orbit. And although this difference is subtle, it demonstrates how even small geometric features can have measurable effects when applied consistently over time. And the elliptical shape of Earth's orbit also means that Earth experiences two key positions known as perihelion when it is closest to the Sun, and aphelion when it is farthest away. And these positions occur at consistent times each year, with perihelion currently happening in early January and aphelion in early July. And this timing often surprises people because it contradicts the common assumption that seasons are caused by changing distance from the Sun. Yet the fact that Earth is closest to the Sun during Northern Hemisphere winter clearly demonstrates that orbital distance is not the primary driver of seasonal temperature change, and instead, the ellipse plays a supporting role, subtly modifying the distribution of solar energy rather than defining it. And from a physical standpoint, the difference in distance between perihelion and aphelion amounts to only about 3% of the average Earth-Sun distance, which translates to a modest change in the amount of solar energy Earth receives. And while this change does slightly intensify Southern Hemisphere summers and Northern Hemisphere winters, due to their alignment with perihelion, its effect is secondary compared to the influence of axial tilt. And the elliptical orbit also affects how solar radiation is distributed over time, because Earth spends slightly more time in the portion of its orbit farther from the Sun, meaning that seasons occurring near aphelion are marginally longer than those near perihelion, and this asymmetry contributes to subtle differences in seasonal duration that can influence long-term climate patterns, agriculture, and ecological timing. And over thousands of years, these effects accumulate and interact with other orbital variations, such as changes in axial tilt and orbital orientation, to shape Earth's climate history. And the elliptical nature of the orbit is therefore a key component of the broader set of cycles known as Milankovitch cycles, which describe how variations in Earth's motion influence ice ages and long-term climate shifts. And although the ellipse itself is stable over short timescales, its orientation slowly rotates in space through a process called apsidal precession, gradually changing the timing of perihelion and aphelion relative to the seasons. And this slow drift means that the relationship between orbital distance and seasonal timing evolves over tens of thousands of years, subtly altering the balance of solar energy between hemispheres and contributing to long-term climate variability. And from a scientific perspective, understanding Earth's elliptical orbit is essential for accurate climate modeling, satellite navigation, and space exploration, because precise knowledge of Earth's position and velocity at any given time allows scientists to predict solar exposure, gravitational interactions, and orbital stability with high accuracy. And this precision underpins everything from weather forecasting to the operation of global positioning systems. And historically, the recognition that Earth's orbit is elliptical represented a major shift in human understanding of the cosmos, moving away from the idea of perfect circular motion as a requirement for celestial harmony and toward a more accurate, evidence-based view of planetary motion governed by universal physical laws. And this shift laid the groundwork for modern astronomy and physics, fundamentally changing how humanity understands its place in the universe. And even today, the near-circular but elliptical nature of Earth's orbit serves as a reminder that natural systems often balance simplicity and complexity, combining stability with subtle variation. And although the ellipse does not dominate seasonal change, it adds nuance to Earth's motion, influencing timing, energy distribution, and long-term climate behavior in ways that become apparent only when viewed across large spatial and temporal scales. And by appreciating the role of Earth's slightly elliptical orbit, we gain a more complete understanding of how predictable cycles emerge from continuous motion, how small deviations can matter over time, and how Earth's journey around the Sun, while gentle and stable, is shaped by precise geometric relationships that quietly but persistently influence the planet's environment, climate, and capacity to support life. Despite Earth's orbit around the Sun being slightly elliptical, variations in distance play only a minor role in shaping seasonal temperature changes, a fact that becomes clear when the geometry of sunlight and the physics of energy distribution are examined carefully. Because the primary driver of seasons is not how close Earth is to the Sun, but how sunlight strikes the planet's surface in terms of angle, duration, and concentration. And the difference between Earth's closest approach to the Sun and its farthest point amounts to only a small fraction of the total Earth-Sun distance, producing a change in incoming solar energy that is measurable but insufficient to explain the dramatic contrasts between summer heat and winter cold. And this realization corrects one of the most persistent misconceptions about seasons, which assumes that warmer temperatures occur simply because Earth is closer to the Sun during summer, when in reality, the northern hemisphere experiences summer when Earth is actually farther away. And this counterintuitive relationship highlights the dominance of axial tilt over orbital distance, because tilt determines how directly sunlight is delivered and how long it remains above the horizon each day. And when sunlight arrives at a steep angle during summer, it concentrates energy into a smaller surface area and persists for longer hours, producing stronger heating even when Earth is slightly farther from the Sun. Whereas in winter, sunlight arrives at a shallow angle, spreading energy over a larger area and remaining above the horizon for fewer hours, reducing heating efficiency even when Earth is slightly closer. And this geometric effect overwhelms the modest influence of distance, making axial orientation the decisive factor in seasonal temperature variation. And from a physical standpoint, the intensity of sunlight per square meter is far more sensitive to angle than to small changes in distance, because angle determines whether energy is focused or diluted across the surface. And this principle can be demonstrated with simple experiments using angled light sources, reinforcing its intuitive validity. And the minor role of distance is further confirmed by global observations, showing that both hemispheres experience opposite seasons simultaneously, despite sharing the same Earth-Sun distance at any given moment. And this hemispheric opposition cannot be explained by distance alone, but is perfectly accounted for by tilt-driven sunlight distribution. And while the elliptical orbit does introduce slight asymmetries, such as marginally stronger southern hemisphere summers due to their alignment with perihelion, these effects are subtle and often masked by other factors such as ocean circulation, land distribution, and atmospheric dynamics. And in practice, regional climate patterns depend far more on latitude, geography, and circulation systems than on small variations in orbital distance. And this understanding is crucial for climate science because it clarifies which variables must be prioritized when modeling seasonal behavior and long-term climate trends. ensuring that emphasis is placed on axial tilt, albedo, greenhouse gases, and energy transport rather than distance fluctuations alone. And historically, recognizing the minor role of distance represented an important step in refining scientific explanations of climate, moving beyond intuitive but incorrect assumptions toward a more accurate, geometry-based understanding of Earth-Sun interactions. And this shift parallels broader developments in science where careful measurement and theory replace surface-level reasoning, and biologically, organisms have evolved to respond primarily to changes in daylight length and sunlight angle, rather than distance, because these cues are reliable and consistent across generations, allowing life to synchronize growth, reproduction, and migration with seasonal cycles that remain stable over long periods. And this evolutionary alignment further demonstrates that distance-based effects are secondary, as they do not provide strong or consistent signals for adaptation. And in human contexts, agricultural calendars, cultural festivals, and seasonal behaviors are likewise aligned with daylight and temperature patterns, rather than any awareness of Earth's distance from the sun, reinforcing the practical irrelevance of distance in everyday seasonal experience. And from a pedagogical perspective, emphasizing the minor role of distance helps prevent misunderstandings and fosters a deeper appreciation of how three-dimensional geometry governs planetary behavior, encouraging learners to think spatially and dynamically rather than relying on simple linear explanations. And this perspective also enhances our understanding of other planets, because it allows scientists to predict seasonal behavior on worlds with different tilts and orbital shapes, recognizing that a highly elliptical orbit may matter greatly on some planets while remaining secondary on others, depending on axial orientation and atmospheric composition. And over very long timescales, changes in orbital eccentricity can amplify or reduce seasonal contrasts by interacting with axial tilt and precession. But even in these cases, distance acts as a modifier rather than a primary driver, shaping the intensity of seasons without creating them outright. And this layered interaction illustrates how Earth's climate system is governed by multiple overlapping cycles that operate together rather than independently. And ultimately, the fact that Earth's distance from the sun plays only a minor role in seasonal temperature changes reveals a deeper truth about the planet's design, showing that stable, life-supporting seasons emerge not from dramatic swings in proximity, but from a precise and enduring orientation in space, where geometry, motion, and energy distribution combine to create predictable rhythms that shape climate, ecosystems, and human life year after year, with remarkable consistency and balance. In fact, Earth is slightly closer to the sun during northern hemisphere winter than during summer, a reality that powerfully illustrates why distance alone cannot explain seasonal temperature changes, and why Earth's axial tilt remains the dominant factor shaping the seasons. Because every year Earth reaches perihelion, the point in its orbit closest to the sun, in early January, a time when much of the northern hemisphere is experiencing winter cold, short days, and low solar angles, while simultaneously the southern hemisphere is in the midst of summer, receiving long days and intense sunlight. And this simultaneous experience of opposite seasons at the same Earth-Sun distance clearly demonstrates that proximity to the sun is not the controlling variable. And the difference in distance at perihelion compared to aphelion is only about 5 million kilometers, a small fraction of the average distance, producing a modest increase in incoming solar energy that is distributed across the entire planet rather than concentrated in one hemisphere. And because this increase is global, it does not override the hemispheric differences created by axial tilt, which determine where sunlight is concentrated and how long it remains above the horizon each day. And as a result, the northern hemisphere remains cold during perihelion because sunlight arrives at a shallow angle and daylight hours are short, while the southern hemisphere experiences summer warmth because sunlight is more direct and prolonged. And this contrast provides one of the clearest natural demonstrations of how angle and duration of sunlight outweigh distance in determining seasonal climate. And from a physical perspective, the slight increase in solar energy at perihelion does have measurable effects, subtly intensifying southern hemisphere summers and slightly moderating northern hemisphere winters. But these effects are relatively small compared to the influence of land-ocean distribution, atmospheric circulation, and heat storage in the oceans, which tend to dominate regional climate outcomes. And the southern hemisphere's greater ocean coverage further dampens temperature extremes, absorbing and redistributing heat more efficiently than land-dominated regions in the northern hemisphere. And this interaction between orbital geometry and surface composition illustrates how multiple factors combine to shape climate rather than any single variable acting alone. And historically, the discovery that Earth is closest to the Sun during northern hemisphere winter challenged intuitive assumptions and helped refine scientific understanding of seasonal mechanics, reinforcing the importance of careful observation and measurement over simple reasoning. And this realization has become a foundational concept in astronomy and earth science education, often serving as a key example used to correct misconceptions about seasons. And biologically, life on Earth has evolved in response to the consistent pattern of axial tilt rather than the timing of perihelion, because tilt-driven cues, such as daylight length, provide reliable signals year after year, whereas distance-related effects are too subtle to serve as primary triggers for biological processes, and plants, animals, and ecosystems therefore remain synchronized with, say, seasonal light cycles regardless of Earth's changing distance from the Sun. And in human experience, the fact that winter occurs when Earth is closest to the Sun often comes as a surprise. Yet it reinforces a deeper appreciation of the planet's three-dimensional motion and the elegance of the mechanisms that govern climate. And from a long-term perspective, the timing of perihelion slowly shifts due to orbital precession, meaning that thousands of years from now, perihelion may occur during a different season, subtly altering hemispheric contrasts and contributing to long-term climate variability. Yet even as this timing changes, axial tilt will continue to define the fundamental structure of seasons, maintaining the familiar rhythm of winter, spring, summer, and autumn. And this persistence highlights the stability of Earth's seasonal system despite gradual orbital evolution. And ultimately, the fact that Earth is closer to the Sun during northern hemisphere winter serves as a compelling reminder that seasons arise not from simple proximity, but from orientation and the distribution of energy across space and time, revealing how a small, tilted planet moving smoothly around its star can generate profound and predictable patterns that shape climate, ecosystems, and human life with remarkable consistency. Seasonal climate patterns strongly influence weather systems, ocean currents, and atmospheric circulation, forming a deeply interconnected global system in which changes in sunlight distribution set off cascading physical responses across the planet's air, water, and land. Because as Earth's axial tilt alters the angle and duration of sunlight through the year, it creates shifting temperature gradients between the equator and the poles, between land and ocean, and between hemispheres, and these gradients are the fundamental drivers of atmospheric motion. Since air naturally moves from regions of higher pressure and lower temperature toward regions of lower pressure and higher temperature, generating winds, storms, and large-scale circulation cells. And during different seasons, these gradients strengthen, weaken, or reverse, reshaping global wind patterns such as the Hadley, Ferrel, and polar cells, which in turn influence precipitation belts, desert formation, and storm tracks. And for example, during summer in a given hemisphere, increased solar heating causes air to rise more vigorously over continents, lowering surface pressure and drawing in moist air from surrounding oceans, often leading to monsoon systems characterized by intense seasonal rainfall. While in winter, the same regions may experience high pressure, dry air, and stable conditions due to reduced heating and descending air. And this seasonal reversal illustrates how sunlight-driven temperature differences directly reorganize atmospheric circulation, and oceans respond in parallel, because surface winds driven by seasonal pressure patterns push ocean water, shaping currents that redistribute heat around the globe, and these currents act as massive thermal conveyors, moderating climate by transporting warm water toward higher latitudes and cold water toward the tropics. And seasonal changes in wind strength and direction can shift ocean currents, upwelling zones, and surface temperatures, influencing marine ecosystems and regional climates. And phenomena such as El Niño and La Niña, while not strictly seasonal, are strongly modulated by seasonal background conditions that determine how ocean-atmosphere interactions unfold. And the timing and intensity of these events depend in part on the seasonal cycle of solar heating, and atmospheric circulation also controls the distribution of moisture, meaning that seasonal patterns determine where and when rain or snow falls, shaping river systems, soil moisture, and vegetation growth. And in many regions, predictable wet and dry seasons emerge not from temperature extremes, but from seasonal shifts in circulation patterns, such as the movement of the intertropical convergence zone toward the hemisphere receiving greater solar heating. And this migration governs rainfall across vast tropical regions, sustaining rainforests, savannas, and agricultural systems. And at higher latitudes, seasonal shifts in the jet stream influence the paths of storms, cold fronts, and heat waves, producing characteristic winter storminess and summer calm or convective activity depending on location. And these atmospheric changes interact with the cryosphere, as seasonal temperature patterns determine where snow and ice form or melt, altering surface reflectivity, or albedo, which in turn feeds back into the climate system by affecting how much sunlight is absorbed or reflected. And this feedback can amplify seasonal contrasts, particularly in polar and high-altitude regions, where snow cover persists longer into spring or forms earlier in autumn, reinforcing cooling, and the oceans likewise store and release heat on seasonal timescales, moderating temperature extremes and introducing a lag between peak solar input and peak surface temperatures, which further influences atmospheric circulation by shifting pressure systems weeks or months after the solstices. And these lags help explain why seasonal weather patterns do not align perfectly with astronomical seasons, adding complexity to climate dynamics. And biologically, the seasonal organization of weather and circulation shapes ecosystems by determining growing seasons, water availability, and habitat conditions. And plants and animals are finely tuned to these patterns, relying on seasonal rains, winds, and temperatures to trigger life cycle events. And disruptions to seasonal climate patterns can therefore have profound ecological consequences, affecting food webs, migration routes, and reproductive success. And human societies are deeply embedded within this system, as agriculture, water management, energy use, and disaster preparedness all depend on the predictability of seasonal weather patterns driven by large-scale circulation. And throughout history, civilizations have flourished or struggled based on their ability to anticipate and adapt to seasonal climate behavior. From monsoon timing to winter severity, and in the modern era, understanding seasonal influences on weather and circulation is essential for forecasting, climate modeling, and assessing the impacts of climate change, because as global temperatures rise, seasonal gradients and circulation patterns may shift, altering rainfall distribution, storm intensity, and ocean current behavior in ways that challenge existing ecological and social systems. And scientists study these seasonal mechanisms to distinguish natural variability from long-term trends, recognizing that climate change does not eliminate seasons but modifies their expression, potentially intensifying some patterns while weakening others. And over geological timescales, changes in Earth's orbit and tilt have altered seasonal climate patterns dramatically, contributing to ice ages and warm periods, by reshaping atmospheric and oceanic circulation, demonstrating that the seasonal engine of climate is powerful enough to transform the planet when its parameters shift. And ultimately, Seasonal climate patterns act as the organizing rhythm of Earth's environmental system, coordinating the movement of air and water, regulating the exchange of energy, and linking the sun's changing position in the sky to the complex dynamic behavior of weather, oceans, ecosystems, and human life, making seasons not merely a backdrop to daily experience, but a fundamental driver of the planet's physical and biological processes. The tilt-driven cycle of seasons shapes ecosystems by controlling plant growth and animal behavior, acting as a fundamental environmental rhythm that synchronizes biological processes with predictable changes in light, temperature, and resource availability. Because Earth's axial tilt governs not only how warm or cold a region becomes, but also how long daylight persists. And these two factors together serve as powerful biological signals that organisms have evolved to sense, interpret, and respond to with remarkable precision. And for plants, seasonal changes in sunlight angle and day length regulate photosynthesis, dormancy, flowering, and seed production, ensuring that growth occurs when energy and water are most available and that vulnerable life stages are avoided during harsh conditions. And as spring arrives in temperate regions, increasing daylight triggers hormonal changes within plants that break winter dormancy, stimulate bud formation, and initiate leaf growth, allowing plants to rapidly exploit rising solar energy, while in autumn, shortening days and cooler temperatures signal the approach of winter, prompting many plants to withdraw nutrients from leaves, form protective tissues, and enter a dormant state that conserves energy until favorable conditions return. And this seasonal choreography is not random but finely tuned to the predictable tilt-driven cycle of light and darkness. And animals are equally dependent on these signals, because seasonal variation determines food availability, shelter conditions, and reproductive success. And many species rely more on day length than temperature as a reliable indicator of seasonal progression, since daylight changes are consistent year to year, regardless of short-term weather fluctuations. And for example, birds use increasing daylight in spring to trigger hormonal changes that prepare them for migration and breeding, ensuring that nesting coincides with peak food abundance for raising young, while decreasing daylight in autumn signals the need to migrate, store fat, or alter behavior in preparation for winter scarcity. And mammals in temperate and polar regions often synchronize breeding cycles so that offspring are born during seasons of abundance, maximizing survival chances. And some species enter hibernation or torpor during winter, reducing metabolic demands when food is scarce and temperatures are low, a strategy directly linked to seasonal energy constraints imposed by Earth's tilt. And even animals that do not migrate or hibernate exhibit seasonal changes in coat thickness, coloration, or behavior, adapting to temperature extremes and changing light conditions. And ecosystems as a whole are structured around these seasonal rhythms, because the timing of plant growth sets the foundation for food webs, determining when herbivores feed, when predators hunt, and when decomposers recycle organic matter. And in many ecosystems, a burst of primary productivity during spring and summer fuels the entire biological community for the year, while winter represents a period of reduced activity and energy flow. And in tropical regions, where temperature variation is smaller, seasonal changes driven by shifts in rainfall and sunlight distribution still regulate ecosystems, producing wet and dry seasons that control plant growth cycles, animal movements, and reproductive timing. And these patterns again trace back to Earth's tilt, which governs the migration of solar heating and atmospheric circulation belts across the globe. And aquatic ecosystems are similarly shaped by seasonal cycles, because changes in sunlight, temperature, and wind influence water stratification, nutrient mixing, and biological productivity in lakes and oceans. And seasonal plankton blooms, for example, form the base of marine food webs and occur in response to increasing sunlight and nutrient availability in spring, supporting fish populations and higher predators. And disruptions to these seasonal cues can have cascading effects, as mismatches between plant growth and animal life cycles can reduce reproductive success and destabilize ecosystems. And this sensitivity highlights how deeply life is intertwined with the tilt-driven seasonal system, and human societies are also embedded in this ecological framework, having historically organized agriculture, hunting, and settlement patterns around predictable seasonal changes, planting crops in spring, harvesting in autumn, and storing food to survive winter scarcity. And many cultural traditions, festivals, and calendars reflect this ecological dependence on seasonal rhythms, celebrating planting, harvest, renewal, and rest. And even in modern technological societies, seasonal cycles continue to influence food production, energy demand, and human health, affecting everything from crop yields to disease patterns and mental well-being. And from an evolutionary perspective, the stability of Earth's axial tilt over long timescales has allowed life to adapt reliably to seasonal variation, fostering biodiversity by creating a wide range of ecological niches defined by seasonal intensity, duration, and predictability. And species distributions across latitudes often reflect tolerance for seasonal extremes, with some organisms thriving in highly seasonal environments, while others specialize in more stable climates. And over geological time, changes in tilt magnitude have altered seasonal contrasts, reshaping ecosystems and driving evolutionary pressures that favor different adaptations, demonstrating that the seasonal system is not merely a backdrop for life, but an active force in shaping its diversity and complexity. And in the context of contemporary climate change, understanding how ecosystems respond to tilt-driven seasonal cues is critical, because warming temperatures can decouple traditional relationships between daylight, temperature, and biological timing, leading to shifts in flowering dates, migration patterns, and species interactions, and these changes can ripple through ecosystems in unpredictable ways, challenging the resilience of natural systems and the human societies that depend on them. And ultimately, the tilt-driven cycle of seasons represents one of the most profound connections between planetary motion and living systems, showing how a simple geometric feature of Earth's orientation in space governs the timing, structure, and rhythm of life itself, coordinating countless biological processes into a coherent, planet-wide pattern that repeats year after year, sustaining ecosystems through balance, adaptation, and predictable change. Many species rely on seasonal cues such as daylight length for migration, reproduction, and hibernation, because photoperiod, the precise length of day and night, provides one of the most reliable and predictable environmental signals available in nature, remaining consistent from year to year regardless of short-term weather variability. And as a result, evolution has strongly favored organisms that use changes in daylight as their primary timing mechanism for critical life cycle events, ensuring that behaviors essential for survival and reproduction occur at the most advantageous moments within the seasonal cycle. And for migratory species, particularly birds, daylight length acts as a biological calendar that initiates complex physiological changes long before environmental conditions visibly shift, triggering hormonal cascades that stimulate appetite, fat accumulation, muscle development, and navigational readiness, allowing these animals to embark on long-distance journeys that align their arrival at breeding or feeding grounds with peak resource availability. And this reliance on photoperiod ensures that migration is anticipatory rather than reactive, reducing the risk of arriving too late to exploit seasonal abundance. And similar mechanisms operate in fish, insects, and mammals that migrate in response to seasonal changes in food supply, temperature, or breeding conditions. And reproduction is equally governed by seasonal cues, because timing the birth or hatching of offspring to coincide with favorable conditions dramatically increases survival rates. And many animals synchronize mating behaviors with increasing or decreasing daylight, ensuring that gestation or development aligns with seasons of warmth, abundant food, and reduced environmental stress. And in temperate regions, longer days in spring stimulate reproductive hormones in birds and mammals, leading to courtship, nesting, and breeding precisely when insects, plants, and other food sources begin to flourish, while in autumn, shortening days suppress reproductive activity and redirect energy toward survival strategies. And hibernation and torpor represent another class of seasonal adaptations driven by daylight cues, particularly in mammals living in regions with harsh winters, where reduced food availability and low temperatures make sustained activity energetically costly. And in these species, decreasing day length initiates metabolic changes that lower body temperature, heart rate, and energy consumption, allowing animals to survive extended periods of scarcity by relying on stored fat reserves. And this physiological transformation is carefully timed so that hibernation begins before resources are fully depleted and ends when conditions improve. And beyond these dramatic behaviors, seasonal cues influence a wide range of subtler biological processes, including changes in fur thickness and coloration, hormone levels, immune function, and even brain structure in some species, reflecting the deep integration of photoperiodic timing within biological systems. And plants, though stationary, also rely on daylight length to regulate flowering, seed germination, and dormancy, ensuring that reproduction occurs during optimal conditions for pollination and seed dispersal. And this synchronization between plant and animal cycles creates tightly linked ecological networks, where the timing of one species' life events depends on those of others. And disruptions to these seasonal cues can therefore cascade through ecosystems, causing mismatches that reduce reproductive success and alter population dynamics. And human-induced environmental changes, particularly climate change, pose challenges to species that rely heavily on photoperiodic cues, because while daylight length remains constant, temperature and weather patterns are shifting, leading to situations where traditional timing based on light no longer perfectly aligns with resource availability. And, for example, some migratory birds now arrive at breeding grounds earlier due to warmer temperatures. Yet the insects they rely on may peak at different times, creating timing mismatches that affect chick survival. And such disruptions highlight the delicate balance between stable astronomical cues and more variable climatic conditions. And humans themselves are not immune to seasonal biological responses, as changes in daylight influence circadian rhythms, hormone production, mood, and sleep patterns, with conditions such as seasonal affective disorder illustrating how deeply photoperiod affects physiology and mental health. And throughout his story, human societies have structured calendars, rituals, and agricultural practices around seasonal cues, recognizing their importance for survival and well-being. And, from an evolutionary perspective, the widespread reliance on daylight length as a timing mechanism underscores the profound influence of Earth's axial tilt on life. Because without predictable seasonal changes in photoperiod, many of the complex behaviors that define ecosystems today might never have evolved. And this dependence also emphasizes the resilience and vulnerability of biological systems. Resilient in their ability to adapt to regular, predictable change, yet vulnerable to disruptions that decouple long-established relationships between light, temperature, and ecological timing. And, ultimately, the reliance of countless species on seasonal cues such as daylight length reveals how life on Earth is intricately synchronized with the planet's motion through space, transforming a simple astronomical pattern into a universal biological rhythm that governs migration, reproduction, dormancy, and survival across the living world. Human civilizations have historically depended on seasonal cycles for agriculture and food planning, because long before modern technology allowed societies to buffer themselves from environmental variability, survival hinged on understanding, predicting, and adapting to the rhythmic changes in climate driven by Earth's axial tilt. And the rise of agriculture itself was inseparable from the recognition that plants grow, mature, and reproduce in response to seasonal patterns of light, temperature, and rainfall, requiring humans to align their activities with these natural cycles in order to secure reliable food supplies. And early agricultural societies learned through observation and experience that planting too early risked frost damage, while planting too late reduced yield. Leading to the development of seasonal calendars based on solar positions, star risings, and recurring environmental cues, such as flowering plants or animal migrations. And these calendars allowed communities to coordinate planting, irrigation, harvesting, and storage with remarkable precision, forming the backbone of stable food production and enabling population growth, specialization of labor, and the emergence of complex societies. And in many regions, the seasonal cycle dictated not only when crops could be grown, but also which crops were viable, shaping regional cuisines, economies, and cultural identities around grains, fruits, and vegetables, adapted to local seasonal conditions, and the dependence on seasons extended beyond planting and harvesting to food preservation strategies. As societies developed techniques such as drying, salting, fermenting, and storing to bridge the gap between periods of abundance and scarcity, particularly in regions with harsh winters or prolonged dry seasons. And these practices were essential for survival during months when fresh food was unavailable, reinforcing the importance of planning ahead based on seasonal expectations. And pastoral societies likewise organized their movements and livestock management around seasonal cycles, migrating herds to follow grazing availability and water sources, demonstrating that seasonal dependence was not limited to farming, but applied broadly to human subsistence strategies. And as civilizations grew, seasonal predictability became embedded in social and political structures, with taxation, trade, labor obligations, and religious rituals often tied to agricultural seasons. And rulers derived legitimacy in part from their ability to ensure food security by managing seasonal risks, such as droughts, floods, or crop failures. And many ancient monuments and ceremonial sites were aligned with solstices and equinoxes, reflecting the central role of seasonal timing in agricultural and spiritual life. And these alignments served both symbolic and practical purposes, reinforcing communal awareness of seasonal transitions and providing reference points for agricultural planning. And even as technology advanced, seasonal cycles continued to shape human life, influencing work patterns, settlement design, and economic rhythms, with winter often associated with reduced agricultural labor and increased indoor activities, while summer demanded intense physical effort in fields, and seasonal food availability shaped diets, health, and cultural traditions, with festivals celebrating planting, harvest, and renewal marking key moments in the agricultural year. And in the modern era, industrialization and global trade have reduced direct dependence on local seasons for food availability, allowing people in many regions to consume out-of-season produce year-round. Yet this apparent independence masks continued reliance on seasonal cycles at larger scales, because global agriculture remains governed by Earth's seasons, with planting and harvest times staggered across hemispheres to supply international markets. And disruptions to seasonal patterns due to climate variability or change can still threaten food security, as seen in crop failures caused by unseasonal frosts, heat waves, or shifting rainfall. And contemporary agricultural science continues to rely on seasonal knowledge, using climate models and historical data to optimize planting schedules, manage water resources, and anticipate pest outbreaks, demonstrating that seasonal planning remains central even in high-tech farming systems. And human biology itself reflects this long history of seasonal dependence, as nutritional needs, disease patterns, and energy expenditure have historically fluctuated with the seasons, influencing cultural practices around food consumption, fasting, and feasting. And in many societies, seasonal foods were valued not only for availability, but for their perceived health benefits at different times of year, reinforcing a holistic understanding of the connection between seasons and well-being. And the cultural memory of seasonal dependence persists in language, traditions, and social norms, even in urbanized societies, reminding people of their agricultural roots and ongoing connection to natural cycles. And from a broader perspective, the historical dependence of human civilizations on seasonal cycles underscores a fundamental truth about humanity's place within Earth's system, namely that despite technological advances, humans remain embedded within the planet's seasonal rhythms, relying on the predictable tilt-driven cycle of light and climate that has governed food production for thousands of years. And as global climate change alters seasonal patterns, this dependence becomes newly visible, challenging societies to adapt agricultural systems, food planning, and resource management to changing conditions, while preserving the stability that seasonal predictability has long provided. And ultimately, the story of human civilization is inseparable from the story of the seasons, because it was the ability to understand, anticipate, and work with seasonal cycles that transformed humans from nomadic foragers into agricultural societies, enabled the growth of cities and cultures, and continues to shape food systems and human survival in an ever-changing world. Seasonal variations affect ice formation, snow cover, and long-term climate patterns by regulating how energy is absorbed, stored, reflected, and redistributed across Earth's surface throughout the year, creating feedback loops that link short-term seasonal change to long-term climate behavior. Because the tilt-driven cycle of sunlight determines when and where temperatures fall below freezing, allowing snow and ice to accumulate, and when melting dominates, returning water to oceans, rivers, and the atmosphere. And this annual advance and retreat of ice is not merely a surface phenomenon, but a powerful climate regulator that influences atmospheric circulation, ocean currents, and the planet's overall energy balance. And during winter in high and mid-latitudes, reduced solar input and shallow sun angles promote cooling, leading to snowfall and the expansion of snow cover and sea ice, particularly in polar regions. And snow and ice have high albedo, meaning they reflect a large fraction of incoming sunlight back into space, rather than absorbing it, which further cools the surface and reinforces winter conditions, creating a positive feedback that strengthens seasonal cold, while in summer, increased sunlight and higher sun angles reduce snow and ice extent, exposing darker land and ocean surfaces that absorb more solar energy, amplifying warming and accelerating melting. And this seasonal albedo contrast plays a critical role in shaping temperature differences between seasons and latitudes. And beyond surface temperature, the presence or absence of ice strongly affects atmospheric circulation patterns, because large ice-covered regions cool the air above them, increasing air density and influencing pressure systems that drive winds and storm tracks. And in winter, extensive snow cover across continents can strengthen high-pressure systems, steering cold air outbreaks and shaping regional weather patterns far beyond the ice itself, while in summer, reduced snow and ice allow more heat exchange between the surface and atmosphere, fueling convection storms and monsoon systems. And the oceans are equally influenced by seasonal ice cycles, particularly in polar regions, where sea ice formation expels salt into surrounding waters, increasing salinity and density, and contributing to deep water formation that drives global ocean circulation. And this process links seasonal freezing directly to the long-term movement of heat around the planet, demonstrating how seasonal processes scale up to influence climate over decades and centuries. And snow cover on land also affects soil temperature, moisture, and hydrology, insulating the ground during winter, and controlling the timing and intensity of spring melt, which feeds rivers, replenishes groundwater, and influences ecosystems and human water supplies. And changes in the timing of snowmelt can alter flood risk, agricultural productivity, and ecosystem dynamics, highlighting the importance of seasonal ice processes for both natural and human systems. And over long timescales, the cumulative effects of seasonal ice formation interact with gradual changes in Earth's orbit and tilt to drive major climate shifts, such as ice ages, because small variations in seasonal sunlight distribution can determine whether snow from one winter fully melts in summer or persists year after year, gradually building large ice sheets. And this sensitivity arises because it is not annual average temperature alone that matters, but the balance between summer melting and winter accumulation, making seasonal intensity a key driver of long-term climate state. And when summers are slightly cooler due to orbital variations, ice can survive and expand, increasing albedo and reinforcing cooling in a self-sustaining cycle, while warmer summers promote ice retreat and a transition toward interglacial conditions. And these processes demonstrate how seasonal dynamics serve as the gateway through which slow astronomical changes influence Earth's climate. And in the modern context, seasonal ice cycles are changing rapidly due to global warming, with reduced snow cover, earlier spring melt, and shrinking sea ice altering the traditional seasonal rhythm, weakening albedo feedbacks, and exposing darker surfaces that absorb more heat, further accelerating warming. And these changes have far-reaching consequences, from amplified warming in polar regions to shifts in weather patterns at lower latitudes, illustrating once again how seasonal processes are tightly coupled to global climate behavior. And human societies feel these impacts through changes in water availability, sea level rise from melting land ice, and increased climate variability, reinforcing the importance of understanding seasonal ice dynamics for adaptation and mitigation strategies. And historically, seasonal ice and snow patterns have shaped human settlement, transportation, and culture, with frozen rivers enabling winter travel, snow cover influencing agriculture and wildlife, and seasonal thaw dictating when land could be cultivated or built upon. And even today, seasonal ice remains a defining feature of many regions, influencing ecosystems, economies, and infrastructure. And at the deepest level, the connection between seasons, ice, and climate reveals how Earth's tilt-driven cycle of light and darkness extends far beyond simple temperature change, acting instead as a fundamental engine that regulates the planet's reflective properties, water cycle, and energy flows, linking the familiar experience of winter snow and summer melt to the grand long-term evolution of Earth's climate system, and reminding us that the patterns we observe each year are part of a much larger, interconnected story that unfolds across centuries and millennia. Over very long time scales, slight changes in Earth's tilt can alter the intensity of seasons by subtly redistributing how sunlight is delivered across latitudes and throughout the year, demonstrating that while the basic seasonal cycle feels stable within a human lifetime, it is actually part of a slow, dynamic system that evolves over tens of thousands of years, because Earth's axial tilt is not fixed at a single value, but gently oscillates within a narrow range, due to gravitational interactions with the Moon, the Sun, and other planets. And these gradual variations, though small in magnitude, have profound consequences for climate, because they directly control how extreme summers and winters become, particularly at high latitudes where ice sheets can either grow or retreat depending on seasonal intensity. And when Earth's tilt is slightly larger, the contrast between seasons increases, producing hotter summers and colder winters, especially in polar and temperate regions, while a smaller tilt reduces seasonal contrast, leading to milder summers and winters with less extreme differences in sunlight and temperature. And this matters enormously for the persistence of snow and ice, because it is the warmth of summer, rather than the cold of winter, that determines whether ice melts away or accumulates year after year. And during periods of lower tilt, cooler summers may fail to fully melt winter snow at high latitudes, allowing ice to gradually build up and expand into massive ice sheets, while periods of higher tilt can intensify summer melting, contributing to ice retreat even if winters are colder. And this asymmetry reveals why small changes in tilt can tip the climate system toward glacial or interglacial states. And these long-term tilt variations operate in concert with other slow orbital changes, creating cycles in seasonal intensity that unfold far beyond the timescale of human history, yet leave unmistakable signatures in geological records, such as ice cores, sediment layers, and fossil distributions. And from a physical standpoint, the mechanism is elegantly simple, because tilt determines the angle at which sunlight strikes Earth's surface and how long it remains above the horizon. And even slight adjustments to this geometry can significantly alter the amount of solar energy received during critical seasons, particularly summer at high latitudes, where ice sensitivity is greatest. And this sensitivity arises because high-latitude regions already receive relatively low annual sunlight, making them especially responsive to changes in seasonal distribution rather than total energy. And as a result, tilt variations disproportionately affect polar regions, amplifying their influence on global climate through feedback processes involving ice, albedo, and atmospheric circulation. And over geological time, these feedbacks have reshaped Earth's climate repeatedly, transforming landscapes, altering sea levels, and driving shifts in ecosystems as ice advanced and retreated across continents. And life on Earth has adapted to these slow rhythms, with species migrating, evolving, or going extinct in response to changing seasonal extremes. And human ancestors, too, were influenced by long-term seasonal variability, as shifting climates altered habitats, food availability, and migration routes, indirectly shaping the course of human evolution and cultural development. And importantly, these tilt-driven changes occur gradually enough that they do not disrupt the fundamental predictability of seasons within a given era, allowing ecosystems and societies time to adapt. Yet they also remind us that Earth's climate system has multiple layers of variability operating simultaneously, from daily and seasonal cycles to multimillennial shifts. And in the modern context, understanding these long-term tilt effects provides crucial perspective on current climate change, because it highlights that while natural variations in tilt can drive significant climate change over tens of thousands of years, the rapid warming observed today is occurring far faster than these natural cycles would predict, underscoring the influence of additional factors beyond slow astronomical forcing. And nevertheless, the study of tilt variations remains essential for interpreting past climates and anticipating how Earth's seasonal system might continue to evolve in the distant future. And this knowledge reinforces a broader understanding of seasons not as static, unchanging features, but as expressions of a living planetary system shaped by motion, gravity, and time. And ultimately, the realization that slight changes in Earth's tilt can alter seasonal intensity over long timescales deepens our appreciation for the delicate balance that governs climate, revealing how small shifts in orientation can cascade into large-scale environmental transformation, and reminding us that the familiar cycle of seasons we experience today is one moment in a much longer story of planetary change that continues to unfold, silently and steadily, across the vast expanse of geological time. Together, Earth's axial tilt and steady orbit create the rhythmic, predictable cycle of seasons that shapes life on the planet by establishing a stable yet dynamic framework in which energy from the sun is distributed in repeating patterns across time and space, allowing physical systems, ecosystems, and living organisms to synchronize their behavior with extraordinary precision. Because Earth's orbit provides the consistent yearly journey around the sun, while the axial tilt determines how sunlight is angled, concentrated, and timed at different latitudes. And it is the interaction between these two factors, rather than either one alone, that produces the familiar progression of spring, summer, autumn, and winter. And this predictability is one of the most important features of Earth's environment, as it creates a reliable rhythm that life can anticipate and adapt to across generations. And from a physical perspective, the steadiness of Earth's orbit ensures that the overall amount of solar energy received each year remains relatively constant, preventing extreme fluctuations that could destabilize climate, while the tilt introduces variation within that stable framework, creating alternating periods of abundance and scarcity that drive seasonal change. And this balance between stability and variation is crucial, because a planet with no tilt would experience minimal seasonal contrast, limiting ecological diversity, while a planet with extreme tilt might face violent seasonal swings that challenge the persistence of complex life. And Earth's moderate tilt places it in a narrow, favorable range where seasonal differences are strong enough to promote biodiversity, but gentle enough to remain predictable and survivable. And this predictability has allowed ecosystems to evolve intricate seasonal strategies, with plants timing germination, flowering, and seed production to coincide with favorable light and temperature conditions, and animals aligning migration, reproduction, and dormancy with seasonal cues such as day length and food availability. And these biological rhythms are not random responses, but finely tuned adaptations shaped by millions of years of exposure to Earth's seasonal cycle. And the reliability of this cycle means that organisms can invest energy in long-term strategies rather than constantly reacting to unpredictable environmental change, fostering ecological complexity and resilience. And human societies have benefited immensely from this same predictability. As agriculture, settlement, and cultural traditions all emerge from the ability to anticipate seasonal change, plan food production, and organize labor around the agricultural year. And even today, modern economies, infrastructure, and social systems continue to operate on seasonal schedules. From planting and harvesting to energy use, tourism, and education, reflecting the deep integration of seasonal rhythms into human life. And beyond biology and culture, the seasonal cycle also shapes Earth's physical systems, influencing atmospheric circulation, ocean currents, and the global water cycle, as shifting temperature gradients drive winds, storms, monsoons, and precipitation patterns that redistribute heat and moisture around the planet, linking seasonal change in one region to weather impacts in another. And this interconnectedness means that the seasonal cycle is not merely a local phenomenon, but a planetary-scale process that coordinates Earth's systems into a coherent whole. And over long timescales, the same tilt and orbit framework provides continuity amid change, allowing gradual variations in tilt and orbital geometry to modulate seasonal intensity without disrupting the fundamental rhythm. And this layered structure of short-term predictability and long-term evolution has allowed life to persist and adapt through ice ages, warm periods, and shifting climates. And in the present era, recognizing the foundational role of Earth's axial tilt and orbit offers important perspective on environmental change because it highlights the difference between natural, slow variations in seasonal patterns and rapid, human-driven alterations that operate outside the planet's long-established rhythms. And understanding this distinction is essential for assessing the scale and significance of modern climate change. And, at a deeper level, the seasonal cycle shaped by tilt and orbit connects everyday human experience to cosmic motion, reminding us that the changing length of days, the warmth of summer, and the cold of winter are direct consequences of Earth's orientation and movement through space. And this realization fosters a sense of continuity between astronomy, climate, and life itself. And ultimately, the rhythmic, predictable cycle of seasons created by Earth's axial tilt and steady orbit is not just a background feature of the planet, but a central organizing principle of life on Earth, structuring time, shaping environments, guiding evolution, and enabling the remarkable diversity and complexity of living systems to flourish within a stable yet ever-changing planetary home.